से अनुरोध है कि अपने सीट पर बैठ जाएं। हम कार्यक्रम का आरंभ करने जा रहे हैं।
A humble request, please switch off your mobile phones or put it on silent.
आप सभी को सुप्रभात, नमस्कार, सुस्वागतम, सुस्वागतम, सुस्वागतम। इस संस्थान के 63वें स्थापना दिवस पर आप सभी को हार्दिक शुभकामनाएं। ताली।
Good morning, everyone. A very, very warm welcome on this auspicious occasion of 63rd Foundation Day of Indian Institute of Tropical Meteorology.
देवियों और सज्जनों, विशिष्ट अतिथियों, सम्मानित वैज्ञानिकों, शोधकर्ताओं, मित्रों, सहकर्मियों और ऑनलाइन प्रतिभागी, मैं अभिषेक गुप्ता और मेरे साथ डॉक्टर अमिता प्रभु, हम बहुत खुशी के साथ भारतीय उष्णदेशीय मौसम विज्ञान संस्थान के 63वें स्थापना दिवस पर आप सभी का हार्दिक स्वागत करते हैं। आज इस शुभ अवसर पर भारतीय उष्णदेशीय मौसम विज्ञान संस्थान की उल्लेखनीय यात्रा का जश्न मनाने के लिए हम सभी यहाँ एकत्रित हुए हैं। यह एक यात्रा है जिसको वायुमंडलीय और जलवायु विज्ञान की दुनिया में नवाचार, उत्कृष्टता और अभूतपूर्व योगदान द्वारा परिभाषित किया जाता है। हमें वैज्ञानिक अनुसंधान को आगे बढ़ाने के लिए IITM के समर्पण और उष्णकटिबंधीय मौसम विज्ञान के भविष्य को आकार देने में इसकी भूमिका सदैव इस संस्थान से जोड़े रखती है। पिछले 6 दशकों से ये संस्थान एक ज्ञान का प्रतीक रहा है। IITM की विरासत हमें सदैव प्रेरित करती रही है। आज भी हम IITM की विरासत का जश्न उसी गर्व और कृतज्ञता के साथ मनाते हैं। तो अपना कार्यक्रम शुरू करने से पहले मैं आपको ये बताना चाहूँगा कि आज की स्थापना दिवस कार्यक्रम को IITM के आधिकारिक YouTube चैनल पर लाइव स्ट्रीम किया जा रहा है, जिससे जो लोग व्यक्तिगत रूप से यहाँ नहीं आ पाए हैं वे ऑनलाइन जुड़कर इस पर्व का हमारे साथ हिस्सा बन सकते हैं।
Greetings, ladies and gentlemen, distinguished guests, esteemed scientists, researchers, friends, colleagues, and online participants. Today, we gather to celebrate the extraordinary journey of IITM, a journey defined by innovation, excellence, and groundbreaking contributions to the world of atmospheric and climate science. As we embark on this special occasion, we are reminded of IITM's dedication to advancing scientific research and its crucial role in shaping the future of tropical meteorology. Over the past 6 decades, this institute has been a beacon of knowledge. The legacy of IITM is one that inspires us all. And today, we celebrate that legacy with pride and gratitude. Now let us move forward and begin our program today. We would like to welcome our esteemed guests to the stage, please. May I kindly invite the Honorable Secretary of the Ministry of Earth Sciences, Dr. M. Ravichandran. So please. The chief guest of today's program, Professor Berrien Moore, Dean, College of Atmospheric and Geographic Sciences, Director, National Weather Center, the University of Oklahoma, Norman, USA. The guest of honor of today's program, Professor S. Anant Krishnan, Senior Scientist at Indian National Science Academy, Adjunct Professor in Savitribai Phule Pune University, and a former Director of Giant Meterwave Radio Telescope, Pune. Dr. R. Krishnan, Director, IITM. Dr. S.T. Pawar, Senior Scientist and Chairman of Foundation Day Committee, IITM. Welcome, sir.
अपनी इस परंपरा के महत्व के अनुसार अब हम इस शुभ कार्य का आरंभ ईश्वर की वंदना के साथ करेंगे। मैं श्रीमान कृष्णा जी से अनुरोध करता हूं कि वह इस मंच पर आएं और गणेश वंदना की प्रस्तुति करें। कृष्णा जी।
Light symbolizes knowledge, and knowledge dispels ignorance. As we embark on today's celebrations, let us illuminate our hearts and minds with the light of wisdom.
प्रथम तुला वंदितो कृपाळा, प्रथम तुला वंदितो कृपाळा, गजानना गणराया, प्रथम तुला वंदितो कृपाळा, गजानना गणराया, प्रथम तुला वंदितो। विघ्न विनाशक गुणीजन पालक, विघ्न विनाशक गुणीजन पालक, विघ्न विनाशक गुणीजन पालक, दुरित तिमिर हारका, दुरित तिमिर हारका, सुखकारक तू दुःख विदारक, सुखकारक तू दुःख विदारक, तूच तुझ्या सारखा, वक्रतुंड ब्रह्मांड नायका, वक्रतुंड ब्रह्मांड नायका, विनायका प्रभुराया, प्रथम तुला वंदितो कृपाळा, प्रथम तुला वंदितो कृपाळा, गजानना गणराया, प्रथम तुला वंदितो।
Thank you, Krishna.
Wow.
After this divine melody of Lord Ganesha that denotes wisdom and light, we now move forward and request our dignitaries to pay homage to the greatest wealth of all, knowledge. May I request our dignitaries to come and join us in lighting the lamp. Thank you so much. May I kindly request our director, Dr. R. Krishnan, to extend a warm welcome to our secretary, Dr. M. Ravichandran, by presenting him with a bouquet. A warm welcome to our guest of honor, Professor S. Anand Krishnan. May I request Director to present him with a bouquet? A very warm welcome to our chief guest, Professor Baring Moore. May I request Director to present him with a bouquet too? Also, I request our Secretary, Sir, Now, may I request Secretary, Sir, Dr. Ravichandran, to extend a warm welcome to our chief guest, Professor Baring Moore, by presenting him with a shawl and an IITM memento. Also, I request Secretary, Sir, to kindly welcome our guest of honor, Professor S. Anand Krishnan, by presenting him too with a shawl and an IITM memento. Thank you, sir. Now, may I again request our director, Dr. R. Krishnan, to felicitate our secretary, sir, with a shawl, please. Thank you, sir. May I now request Dr. S.D. Pawar, Senior Scientist IITM, to welcome our director with a bouquet. Also, may I request Dr. S.D. Pawar to welcome Vice Chancellor, SPPU, Savitribai Phule, Pune University, Professor Suresh Gosavi, with a bouquet, please. I also request Dr. S.D. Pawar to welcome a senior official, Professor Tirumalai Venkatesan from Oklahoma University, with a bouquet. Thank you, sir. Please take your seat, sir. And now, may I request Dr. Abhishek Gupta to welcome Dr. S.D. Pawar with a bouquet. Thank you. Now, it is my privilege to invite our director, Dr. R. Krishnan, to deliver the welcome address to the IITM family. Under his visionary leadership, IITM continues to scale new heights, and we are truly honored to have him address the esteemed gathering. Dr. R. Krishnan, please.
Respected, esteemed dignitaries, Dr. M. Ravichandran, Secretary, Ministry of Earth Sciences, Government of India. Today's chief guest, Professor Berrien Moore, Director, National Weather Center, Dean, College of Atmospheric and Geographic Sciences, Oklahoma University. Guest of honor, Professor S. Ananthakrishnan, INSA Senior Scientist, Adjunct Professor Savitribai Phule, Pune University, and former Director, Giant Meter Wave Radio Telescope, GMRT, National Center for Radio Astronomy, Pune, Dr. S.D. Pawar, Project Director, Atmospheric Electricity and Thunderstorm Dynamics Program, Dr. A.K. Kamra, INSA Emeritus Scientist, and all the esteemed dignitaries of the stage, galaxy of distinguished delegates and participants, present and past members of the IITM family, well-wishers and colleagues, as well as the participants who have joined online. Greetings and warm welcome to all of you on this important occasion of the 63rd Foundation Day celebrations of IITM. Many thanks for accepting our kind invitation to grace this occasion. 63 years back, the institute was founded as Institute of Tropical Meteorology, ITM, on 17 November 1962 as a distinct research and development unit of the India Meteorological Department required for improving operational weather forecasts in the country. Later, the institute acquired status as an autonomous research institute and was renamed as Indian Institute of Tropical Meteorology, IITM, in April 1971. With the vision to be a global center of excellence through basic research and development on all aspects of the tropical atmosphere-ocean coupled system required to improve weather and climate forecasts, IITM has risen to this cause by delving into a diverse range of topics, each contributing to our holistic comprehension of the Earth's climate system and cutting-edge scientific problems in tropical meteorology and atmospheric sciences. The roadmap for achieving this vision of IITM has relied on continuously enhancing the following three components of the institute: scientific understanding, infrastructure development, and human resource development. Below are some key highlights from IITM over the last 1 year. Our Honorable Prime Minister of India, Shri Narendra Modi ji, inaugurated the launch of high-performance computing systems tailored for weather and climate research and operations located at two key sites. One is IITM Pune and the other one at the National Center for Medium Range Forecasting at Noida on 26 September 2024. These state-of-the-art systems have been named as Arka and Arunika. The IITM system is equipped with a capacity of 11.77 petaflops and 33 petabytes of storage, while the NCMRWF facility features 8.24 petaflops and 24 petabytes of storage. Additionally, there is a dedicated standalone system for artificial intelligence and machine learning applications with a capacity of 1.9 petaflops. The enhanced HPC capability will allow us to refine the horizontal resolution of global weather prediction models to an impressive 6 kilometers. Further, regional models will achieve even finer resolutions of 1 kilometer or less over the Indian region, which will significantly enhance the accuracy and lead time predictions of related to tropical cyclones, heavy precipitation, thunderstorms, hailstorms, heat waves, droughts, extreme weather phenomena, as well as air quality forecasts. In addition, the HPC at IITM will greatly benefit the modeling and predictions of monsoons on the subseasonal to seasonal timescale, the S2S scales, decadal predictions, and climate change projections using fully coupled models or Earth system models. IITM is one of the key organizations in the recently launched Mission Mausam by the Ministry of Earth Sciences, Government of India, which is a transformative initiative aimed towards a weather-ready and climate-smart India. This is the Viksit Bharat. The overarching goal of this mission, Mausam mission, is to improve the accuracy of weather, climate, and air quality forecasts across spatial and temporal scales by strengthening observations and integrating them into a state-of-the-art unified Earth system model being developed in India under Mission Mausam. Additionally, Mission Mausam aims to develop capabilities for weather modification research for the benefit of society and humanity. The Atmospheric Research Testbed Central India ART-CI facility located at Silkeda near Bhopal was inaugurated by Honorable Union Minister of Earth Sciences Shri Kiren Rijiju on 12th March 2024. Several state-of-the-art instruments, including a C-band radar, have been installed at ART-CI for atmospheric measurements. Special observational campaigns were conducted jointly with IMD during the 2023 and 2024 monsoon seasons from ART Central India. As part of these campaigns, twice daily radio sonde measurements were conducted in 2023 and 4 times daily radio sonde measurements were conducted in 2024. Additionally, observations using the dual polarization C-band Doppler weather radar, microwave radiometer profiler were made in these monsoon campaigns and shared with NCMRWF for data assimilation. IITM has also established India's first urban radar network over Mumbai metropolitan region, which was inaugurated by Dr. M. Ravichandran, Secretary, Ministry of Earth Sciences, on 14 September 2024 in Kolaba, Mumbai. The Mumbai Urban Radar Network comprises of 4 X-band polarimetric scanning radars, which are separated by a distance of approximately 30 kilometers and located in Panvel, Ville Parle, Vasai Virar, and Kalyan Dombivili. The Mumbai Urban Radar Network data is being shared with IMD for operational requirements. Another new X-band radar is being currently installed at the High Altitude Cloud Physics Laboratory, HACPL Mahabaleshwar, which is expected to be completed around January or February 2025. Here I would like to specially thank Professor Ananthakrishnan, our today's guest of honor, for his valuable guidance in technical matters of this radar. The Mahabaleshwar radar, together with the Mumbai Urban Radar Network, will be an important tool for understanding and nowcasting of severe weather events over the Western Ghats and adjoining areas. IITM established a Climate Data Archival and Distribution System (CDAS) server, which is an Earth System Grid Federation node for dissemination of climate change projections from the Coupled Model Intercomparison Project CMIP-7 for the next IPCC assessment AR7. The CDAS server with 2 petabyte capacity at IITM was inaugurated by Dr. M. Ravichandran, Honorable Secretary, MOES, on 26 September 2024. IITM has added 8 new lightning location network sensors, LLN sensors, to the existing network in different locations in India for monitoring lightning activities. With this recent addition, a total of 92 LLN sensors have been connected to the network. Lightning alerts are being disseminated through mobile app in 15 regional languages. During 2023, IITM researchers published 183 papers in peer-reviewed journals with a cumulative impact factor of 911 and an average impact factor of 5, and 14 PhDs were awarded from IITM. We expect that the number of publications and PhDs from IITM during 2023 will be during 2024 will be comparable to that of 2023. A major international workshop, STIPMEX, was conducted at IITM during June 2024 to assess the influence of stratosphere-troposphere interactions on extreme weather against the backdrop of frequent extreme weather events and to explore future pathways for prediction of monsoon weather extremes. The STIPMEX workshop, jointly organized by IITM, MOES, WCRP, that is the World Climate Research Program, SPARC, Stratosphere, Troposphere Processes and their role in climate, and WWRP, the World Weather Research Program, WMO, was attended by 301 participants from different countries, along with 500 online participants. During March 2025, IITM will be hosting the 8th WMO International Workshop on Monsoons, IWM 8, jointly with Ministry of Earth Sciences and the WWRP's Working Group on Tropical Meteorology Research, WGTMR, in cooperation with IMD, the IMPO, the International Monsoons Project Office, and the Clivar-Juex Monsoon Panel of the World Climate Research Program. Overall, the research and academic endeavors undertaken by IITM underscores the Institute's commitment to advancing our understanding of the tropical atmospheric processes, phenomena, and their wide-ranging impacts required for improving weather and climate forecasts for the betterment of society. All these advances and achievements were possible due to the collective efforts of our scientific, administrative, technical, and support staff, including PhD students, postdoc researchers, and project scientists. I extend my heartiest congratulations and sincerely thank the entire IITM family, the present and the past employees of the Institute for their excellent contributions and dedicated efforts. I am confident that IITM's achievements and contributions will reach greater heights in the years to come. I express my deep gratitude to the Ministry of Earth Sciences, Government of India for the unwavering support and patronage, as well as the IITM Society, the Governing Body, Finance Committee, and the Research Advisory Committee for extending valuable guidance. Without taking much time, I once again thank all of you and welcome all of you to the IITM 63rd Foundation Day celebrations. Thank you all. Jai Hind.
Thank you, sir, for your warm welcome address and inspiring words. Now let's move forward and dive into our next exciting segment. IITM has an atmospheric electricity observatory established by Dr. A.K. Kamra. Today, on this special occasion, we are honored to name this observatory in tribute to the legendary Dr. A.K. Kamra in recognition of his exemplary work in the field of atmospheric electricity. I request Dr. Ravichandran, sir, to officially name the observatory as Dr. A.K. Kamra Atmospheric Electricity Observatory by pressing the button. May we request Dr. A.K. Kamra to come onto the stage, please? Kamra, sir. Yes, sir. We are waiting for Kamra, sir. Okay. He's coming. Let's give a big round of thunderous applause, everyone. Dr. A.K. Kamra. May I request? May I request Kamra sir to officially name the observatory as Dr. A.K. Kamra Atmospheric Electricity Observatory by pressing the button. Let the applause keep coming. seated.
Please be seated.
May I request Secretary Sir to felicitate Dr. A.K. Kamra with a shawl, IITM memento and a bouquet. Please be seated. May I request Kamra sir to be seated downstairs? Please escort Dr. A.K. Kamra to his seat, please. Thank you so much, sir. Now, may I request Professor Pradeep Kumar, Honorary Adjunct Professor from Savitribai Phule Pune University, to share a few words about Dr. Kamra's contributions. Professor Pradeep Kumar has established a cold cloud laboratory at SPPU to study the role of electrical forces within clouds. Professor Pradeep Kumar, please.
Dignitaries on the dais, and my Guru Bhai, Dr. Adarsh Kumar Kamra. I first heard about Dr. Adarsh Kumar Kamra, A.K. Kamra as he is known, nearly 45 years ago from my teacher, late Professor N.C. Varshnia, when I was MSc Physics student at IIT Roorkee. Professor Varshnia was a PhD advisor of Dr. Kamra, and he told us about the instruments that Dr. Kamra had built and the observations he had carried out at Roorkee. Dr. Kamra's family moved to Haridwar from the undivided Punjab during the partition of India. They had their agricultural land, and his father was a teacher, and he was 3 years old when they moved to Haridwar. His father then became a vice principal of the Inter College in Haridwar. Dr. Kamra had his early education and BSc in Haridwar, and then he moved to Dehradun DAV College for his MSc in physics, and then later to IIT Roorkee for his PhD. How Dr. Kamra decided to come into the field of atmospheric electricity is still a mystery to me. For that, I must talk about his PhD advisor. Professor N.C. Varshnia, late Professor N.C. Varshnia, was a high-energy physicist, having done his PhD at Max Planck, Göttingen, and was closely associated with a Nobel laureate. He was an associate professor at IIT Roorkee and used to go to Kodaikanal in the summer for his work on high-energy physics. Here he got interested in clouds and atmospheric electricity. Dr. Kamra, a fresh MSc student, was looking for a PhD advisor and met Professor Varshnia, who told him, quote, "I do not know anything about this field, and if you are willing to work with me, we both will learn together." Professor Varshnia later, he made a name for himself and was elected as a member of International Commission on Atmospheric Electricity. His contribution was very huge. So whether it was a challenge of venturing into the unknown with a supervisor who had no clue on the subject, or the reputation of soft-spoken Professor Varshnia that excited Dr. Kamra to venture into the field of fair weather electricity, still puzzles me. His PhD thesis went for evaluation to Professor Bernard Vonnegut at State University of New York at Albany. Professor Vonnegut was a giant in the field. He is the one who, way back in 1948, along with Vincent Schaeffer, patented the silver iodide for cloud seeding. So along with the thesis report, Professor Vonnegut sent a postdoc offer for Dr. Kamra, so which speaks volumes about the work which Dr. Kamra had done. His work with Professor Vonnegut was on laboratory studies on particle collisions for understanding the electrification of dust storms and thunderstorm electrification and the effect of electric fields on cloud droplets, especially on the phenomena of rain gush. Dr. Kamra is known for designing and carrying out measurements of atmospheric electricity with the instruments he himself has built. Measurement of fair weather electrical parameters is extremely difficult because of the very low currents, which are of the order of picoamperes, and very low charges, which range from nanocoulomb to femtocoulomb. So it's measuring these low charges is an extremely challenging, and he's known for designing and carrying out this extremely difficult measurement. He has designed instruments for measuring almost all the components of fair weather atmospheric electricity, starting with electric field and point discharge currents for his PhD, and then moving on to ions, electrical conductivity, air-earth currents, and space charge. Having worked on all components of fair weather atmospheric electricity, he could not ignore the disturbed weather electricity which drives the global electric circuit. Here he worked on a variety of aspects of thunderstorms, like understanding the lower pocket positive charge, end of storm oscillations, electric fields of lightning, which is important for designing the lightning location systems. And the place where he did his postdocs, SUNY, which is the State University of New York, that was a pioneer in designing the lightning location systems. Over the last 6 decades, he has shown that one can do high-quality research with low-cost home-built instruments, and that too with very good precision. With each of his students, he has built different instruments and has taught them how to carry out meticulous research. Dr. Ravichandran is one of his students. He appears to be tough from the outside, a strict and disciplined taskmaster, but very affectionate from the inside, and that is why all his students have very high regard and respect for him. Even with his physical disability, which he developed due to a brain surgery he underwent in the late 1980s, he has pursued his research goals with the same vigor and energy as before. That speaks volumes about the dedication of Dr. Kamra towards his students and research work. He has guided 8 PhD students, and most of them have graduated after his brain surgery. Sir, it has been an honor and privilege for me to have been closely associated with you for almost 4 decades, starting first as my PhD examiner in 1985. I was fortunate to have closely worked with Dr. Kamra on several advisory committees of DST, IMD, and IITM, co-directed with him 2 SCRC schools on clouds and cloud physics and atmospheric electricity, during which I have learned a lot from him. He is a very good teacher. We have traveled together for several meetings, and I have observed that he has a very, very good sense of humor, which it doesn't appear when you talk to him for the first time. I'm very happy that after completing 80 revolutions around the sun, IITM is recognizing your contributions to the field of atmospheric electricity and your association with IITM for 50 long years. He joined IITM in 1974. I wish you a very good health, and I'm sure that you will be producing several more interesting research articles in years to come.
Thank you so much, Pradeep Kumar sir. We also have a short video highlighting Dr. A.K. Kamra's contributions to the field of atmospheric electricity.
Every year, lightning strikes claim thousands of lives around the world, with India experiencing one of the highest fatality rates due to its vast and varied climate. From rural farming regions to densely populated urban areas, the danger posed by lightning is pervasive. Often catching people outdoors and unprotected, these deadly strikes not only lead to tragic loss of life, but also cause widespread damage to property, agriculture, and critical infrastructure. The pressing need to better understand, predict, and mitigate the impact of lightning has become paramount in reducing casualties and protecting vulnerable communities across India. In India, this essential field of study took root in the 1970s thanks to the pioneering research of Dr. Adarsh Kumar Kamra. Dr. Kamra's groundbreaking work laid the foundation for advancements in measuring and analyzing atmospheric electrical phenomena, establishing methods that continue to drive forward India's capabilities in lightning prediction, weather modeling, and hazard preparedness. His legacy remains instrumental to the evolving field of atmospheric electricity research in India and globally. Dr. A.K. Kamra completed his BSc and MSc at Agra University, pursued a PhD at the University of Roorkee, and conducted postdoctoral research under B. Vonnegut at SUNY Albany. Returning to India, he joined IITM Pune in 1974, rising to Scientist G and continuing as Emeritus Scientist after his 2006 retirement. Dr. A.K. Kamra's career is distinguished by numerous prestigious accolades, including the Indian Academy Council Fellowship 1998, INSA Fellowship 2004, and the IITM Silver Jubilee Award 2007. His expertise led to key roles in scientific committees for CSIR, INSA, and the STORM and CTCZ projects, highlighting his profound impact on atmospheric science in India. Dr. Kamra's groundbreaking contributions include the development of essential instruments for atmospheric electricity research. His innovations like Guardian's apparatus, inverted field mill, particle charge measuring apparatus, space charge tube have paved the way for advancement of lightning and aerosol studies in India and beyond. These instruments have allowed IITM monitor lightning, charge density, and atmospheric ions with precision, establishing IITM Observatory as a world-class center, one of its kind in India and among very few globally. One of Dr. Kamra's significant contributions is the design, fabrication, and installation of a vertical wind tunnel. This indigenously developed tunnel has enabled crucial stimulation experiments to study the interactions between the electrical properties of clouds and their microphysical characteristics. Remarkably, this facility has been in operation for nearly 40 years.
It is an honor and privilege to speak about Dr. Kamra, my mentor and PhD supervisor. His dedication, hard work, and unwavering commitment to the pursuit of scientific knowledge set him apart as an inspiring figure in the academic world. I consider myself fortunate to have had the opportunity to learn and work under his guidance. Dr. Kamra is renowned for his expertise in atmospheric electricity, cloud electrification studies, cloud microphysics, and aerosol physics. He has established a world-class atmospheric electricity laboratory which is truly unique in its capacity and capabilities. Dr. Kamra is instrumental in fabricating, developing, and installing a wide range of instruments to measure various atmospheric electricity parameters installed in the observatory, including the wind tunnel, with available resources at IITM and also using the workshop IITM. His work exemplifies the perfect blend of experimental and theoretical proficiency, making him a true reservoir of knowledge in the field. Words fall short when it comes to expressing Dr. Kamra's enthusiasm, simplicity, and dedication, as well as his ability to motivate colleagues and students to learn and innovate. His passion for research is truly infectious, inspiring all those who have the privilege of working with him. I sincerely wish that he continues to make significant contribution to his field for many more years, blessed with sound health and boundless energy. Thank you.
It is indeed a great pleasure and honor that the Atmospheric Electricity Observatory at IITM Pune is being named as Dr. A.K. Kamra Atmospheric Electricity Observatory in recognition of the outstanding contributions of Dr. A.K. Kamra, who pioneered scientific studies on atmospheric electrical phenomena in India through systematic and innovative measurement
techniques.
Dr. Kamra's research has transformed atmospheric electricity studies in India, greatly enhancing our understanding of lightning formation and behavior. These contributions have significantly improved lightning forecasting accuracy, supporting weather models that predict storm behavior with better precision. As a result, his work has strengthened our ability to mitigate risks associated with lightning, directly contributing to public safety and disaster management strategies in India and advancing global knowledge on storm dynamics.
We have learned many things from Dr. Kamra. I would like to mention few of them here, like his passion for learning new things, his dedication to research work, and most importantly, his presentation with perfection and clarity. He always insisted her to look for the quality, not for the quantity, and therefore we could publish some good quality research work. I feel very fortunate to have him as my research guide, and I really enjoyed working with him.
A group of scientists working in atmospheric electricity in this institute have produced some significant and important results during the last few decades. Main area of thrust in their studies is the interaction of cloud electrification with the microphysics and dynamics of clouds. Both theoretical studies and simulation of these events in a local wind tunnel developed by this institute has given some wonderful results. Another important asset developed in the institute is a world-class atmospheric electricity observatory on atmospheric electricity. In this observatory, a lot of conventional and new instruments developed by the institute scientists were deployed, and observations were continued for several years. Institute scientists have participated extensively under national and international programs in Indian Ocean, Southern Indian Ocean, and Antarctica, and Bay of Bengal, and Arabian Sea, and to have data on particle formation studies and global electrical circuit. Of late, these scientists are involved in studying the lightning climatology information on the South Indian Ocean, in Asia or India in particular. This information is very useful for changing climate scenario and extreme events.
Dr. A.K. Kamra Electricity Observatory, honoring a legacy that continues to save lives and inspire discovery.
May I now request Dr. Ravi Chandran, Secretary Sir, to officially release the booklet on Dr. A.K. Kamra's Atmospheric Electricity Observatory. Thank you. Please be seated.
अब इस सेरेमनी के बाद यहाँ पे बैठे सभी लोग कितने उत्साहित हैं इस सेरेमनी के बाद, मैं बताना चाहूँगा। यही हमारे IITM की सुंदरता है। इस सुंदरता को आगे लेते हुए मैं सिर्फ एक लाइन कहना चाहूँगा कि बाहर मौसम का मिजाज और अंदर बैठे हुए सभी लोगों का अंदाज बस देखते ही बनता है। मैं चाहता हूँ इसी के साथ आप लोग हंसते रहिए, मुस्कुराते रहिए। इसी क्रम में आगे बढ़ते हुए अब मैं इस सभा में उद्घाटन भाषण देने हेतु पृथ्वी विज्ञान मंत्रालय के माननीय सचिव डॉक्टर M. रविचंद्रन को आमंत्रित करता हूं। वो आएं और अपने विचारों से हमें अनुग्रहित करें। सर।
Today's chief guest, Dr. Perrin Moore, and guest of honor, Dr. Ananthakrishnan, Dr. Krishnan, IITM Director, and my mentor and guide, Dr. A.K. Kamra, Professor Suresh Kosavi, and Professor Venkateshan, and Dr. Pawar, and my colleagues and friends from IITM and also Ministry of Earth Sciences and various invitees and friends. Very good morning to all of you. And first and foremost, greetings to all IITM colleagues on the 63rd Foundation Day of IITM. And congratulations to all of you for the immense contribution to the science of atmosphere. I think you have started contributing, especially over the last few decades. I think your contributions were very immense. In the time scale, if I talk about, you start from seconds and milliseconds like lightning, and also you go with the climate scale, with the large, maybe paleo time scales. So in between, you started with the diurnal variation, you have contributed, short-term forecast, you have contributed with the various resolutions of model. Now you have come up to 6 kilometers. And also you have contributed to the what is called extended range forecast, and very important milestone paradigm shift you have made for seasonal forecast under monsoon mission. And also you have made contribution to significantly to the IPCC report. I think all these things speaks volume about you, and also you have made significant remark in terms of observations both in Mahabaleshwar as well as in Bhopal to understand the various processes of the clouds and the atmosphere. I think this contribution is really very important because it is a complex. Of course, atmosphere is always complex. When you learn something, something also changing. So day by day you have to learn much more than the things what is happening over the period. I think considering the importance, of course, now whatever we have done, it is very good. I sincerely appreciate, and each one of you, I thank you for your contribution as well as I appreciate. Having said that, I think a lot more to be done because the weather phenomena, weather forecast, still we need to do much more. We need to understand more, we need to observe more, and also we need to forecast in better accuracy. For that, it is important that your contribution is very, very important. So that is the reason why I think we have started now the Mission Mausam. I think I personally thank each one of you who has contributed the Mission Mausam, especially the document. It is you made the document. I think this document is very important. I can proudly say that this document, full document I have not gone through, but I got glimpses of what is the document said about. I have made one day presentation to Honorable Prime Minister. He told, why you are waiting? Go ahead. I think this is one of the first cabinet approval, within a week, everything, EFC, cabinet approval, everything is done within a week. So that shows the importance of the government in terms of weather importance, because the weather playing a critical role now, we need to work more. So I think it is also appreciation as well as we have to work more. I think in the mission Mausam, we have some of the things we need to observe more. I think with not only institute but also remote sensing with the satellites as well as the radar, mainly radar, not only in the horizontal as well as vertical, all the parameters we need to monitor, so that we need to go for better forecast. So the objective is maybe the next 5 years, maybe we need to develop the infrastructure requirement for the future. Maybe the future means everybody knows that in 2047 we have an aim in terms of our domain. To fulfill that, what is the infrastructure required? So that infrastructure we have to build in within 5 years, so that we can do more science and innovation and other things will follow. So for that reason, I think please aim for more and more infrastructure development in the next 5 years. And also we need to have a greater goal, which what is called ultimately we have to deliver in 2047. I think for infrastructure development, I think government is definitely will whatever we require in terms of manpower as well as the budget required, definitely they will provide, and I think we need to come little bit elevated level so that we need to contribute, because the expectation also very high, and also not only expectation but also the complexity also very high. Actually, maybe earlier we were thinking of even our own field, we can talk earlier, they were thinking about electrometer will say about the weather in the future. Later on, this atmospheric electricity, it was become dull. But now over the period, now it is picking up too much because the clouds are developing vertically very high. So the electrical forces also contribution is much more now. So we need to understand better the cloud physics. So we have equipped, or maybe in IITM or anything, you have significantly contributed the science, new insights, many things in the atmosphere. But at the same time, you have done many things on the modeling. But I think we need to go, we have to change our gear, not only modeling, but also model. We need to contribute to the model. I know that you know the difference between modeling and model. So the model we need to develop. That means we need to, model means I am not telling about modeling. Model, entire model. Parameters and scheme is the key. That is the engine of the car, like that. So I think this engine we need to touch and we need to improve. Maybe the parameters and scheme which we need to develop, thereby we need to contribute significantly. It is not required from the scratch we need to develop the model, but we need to, especially in the tropical region, how the parameter and scheme works, we need to understand. For that, we need to understand more and more cloud physics, cloud microphysics, and various forces acting on that. So I think we need to do again with the experimental work and try to implement whatever we learn in the model so that we can go for better forecasts. So I think I personally feel that I am definitely, especially those who are youngsters, those who will be in 2047, think maybe discuss and think yourself what you can achieve in 2004. For that, how do we evolve over the period? So continuously you can think and you can provide advices, as well as also we have many expertise and experienced people from IITM. I could see many of our colleagues from IITM, earlier they were working, so you can take their advice too. And one important point is we need to collaborate more. To whom to collaborate, no need to say. Within the department, within the ministry, within the IITM, various group, you need to discuss, you need to sit and talk to each other, so that I think when you grow older, we will have more and more ego. So we have to suppress that and we have to discuss among ourselves, especially you put a younger colleague as a catalyst, so they will do what is we need to discuss. And also we need to discuss with the interministerial, and also very importantly, we need to involve academia and also industries. So this is what in Indian scenario we need to follow. So various institutions, academia and industry. So apart from that, we need to collaborate with the international partners. So we need to work with the various universities, or maybe whomever is working in this field. So we need to collaborate with them so we can try to build a rapport and we can work closely so that we can learn each other, so that we can improve our modeling. So my sincere request and advice is, please collaborate as much as possible. Definitely we can learn more and more, and we can contribute to the science so that we can ultimately transform that science to this benefit of society in terms of services. With this, I once again thank you for inviting me. I wish you all for the next decade and further decade, everybody think of 2047. Definitely we need to contribute much more. So wish you all the best. Thank you very much.
सर, इस महत्वपूर्ण अवसर पर IITM को आपकी हार्दिक शुभकामनाओं और अटूट समर्थन के लिए धन्यवाद। आपके शब्द निसंदेह हमें प्रेरित करते रहेंगे और मंत्रालय द्वारा हमें सौंपे गए लक्ष्यों और दृष्टिकोण को प्राप्त करने में हमारे संकल्प को मजबूती प्रदान करेंगे। थैंक यू सर। अब मैं सभा को IITM की गतिविधियों के बारे में जानकारी देने के लिए वरिष्ठ वैज्ञानिक डॉक्टर जे संजय को मंच पर आमंत्रित करता हूं। सर।
Good morning, all. Now, on behalf of Director IITM, I will now briefly highlight few significant events and activities organized at the IITM over the last 1 year. A mini workshop was conducted during second week of February 2024 at IITM to deliberate and compile the MOA's vision document for Vikasit Bharat at 2047 during the Amrit Kal. The workshop aimed to identify key trust areas for MOAs with detailed deliverables and pathways to achieve them. The participants in this mini workshop included representatives nominated from MOAs institutions and experts from other scientific institutions. Dr. M. Ravichandran, Secretary, Ministry of Earth Sciences, provided an introduction to the MOA's vision document for Vikasit Bharat at 2047. The mini workshop was chaired by Professor J. Shukla, Distinguished University Professor at George Mason University, USA, and was co-chaired and hosted by Director IITM. The discussions were conducted in two parts. First, the overall vision for MOAs was deliberated in a plenary session with all the attendees. During this, 4 areas were identified for detailed discussions. The group was then split into 4 breakout groups according to the attendees' expertise, and feedback from individual breakout groups was discussed in a plenary, and accordingly, the recommendations were prepared for the MOA's Vision 2030 and 2047. Now I'll briefly mention some of the noteworthy scientific research outcomes and accomplishments over the past year. Under the monsoon mission, the genesis, track, intensity, and landfall of the severe cyclonic storm Rimal over the Bay of Bengal was forecast with a long lead time of 5 to 6 days by the GEFS T1534 ensemble forecasting system, and the forecasts were shared with IMD. The high resolution global forecast model at 6.5 kilometer, which is being run experimentally, also shows good fidelity in capturing the cyclone genesis and track. Operational seasonal forecast system using the monsoon mission climate forecast system developed at IITM and operationally adopted by IMD are being carried out at IMD with support from IITM. The Climate Variability and Prediction Group has developed the first version of the IITM Decadal Climate Prediction System. Decadal hindcasts and forecasts prepared from 1950 to 2023 are made available to the WMO Lead Center for Global Annual to Decadal Climate. The Center for Climate Change Research started preparations for the couple model intercomparison project, the 7th phase, using the latest version of the IITM Earth System model, version 3, at a TCO 126 atmospheric model resolution, which is around 67 kilometer on Gaussian grid, and high resolution global model at 0.25 degree near equator. And also preparation has started for contributing to the IPCC next assessment report, the 7th assessment report AR7. Global high resolution projections at T574, which is at a 27 kilometer grid, were generated using the atmospheric version of the IITM ESM and CMIP6 boundary conditions. Several observational studies were conducted, including the greenhouse gas flux measurements at Kasiranga National Park and Pichavaram mangroves, at Aris Nainital and Koringa in Kakinada, and also at the Atmospheric Research Testbed Facility in central India near Bhopal. High altitude balloon sonde measurements of water vapor, ozone, and aerosol backscatter from Nainital, and also measurements of land surface parameters, soil moisture, water isotopes, atmospheric trace gases, and short-lived halogens across various locations around the world also was carried out. Fundamental atmospheric chemistry studies were carried out, including quantification of radiative impacts of short-lived halogen chemistry. New reactions of mercury in the atmosphere were discovered. Reduction in the uncertainty of the impact of sulfur emissions of oceans on the radiative budget of the atmosphere was quantified, and also contribution of shipping emissions to atmospheric composition was assessed. Under lower atmospheric research using unmanned aerial system facility, field campaigns were conducted for profiling the atmospheric boundary layer at Osmanabad. The Northeast India Observational Network project has been started during the past year. Under this observational program, various instruments including an impact distrometer, at automatic rain gauge, rainwater collector, and micro rain radar has been installed at the radar facility in Guwahati University, Assam. Installation of 4 automatic rain gauges and rainwater collectors was completed in Arunachal Pradesh. The Fluid Dynamic Laboratory at IITM has developed a universal drag model for smooth wall-bounded turbulent flows, and studies were conducted on generalized scaling and model for friction in wall turbulence. The KIPEX report, titled General Document on Common Questions and Answers on Cloud Seeding, has been published in English, Hindi, Bengali, and Marathi, and is available online on the IITM website. IITM participated in the India's maiden Arctic winter expedition, which was launched by the Honorable Minister of Ministry of Earth Sciences. IITM successfully installed an electric field mill and Maxwell current antenna at the Himadri site. Also, continuous observation of modeling and activities on air quality is continuing to support the decision support system for air quality forecasting and mitigation in Delhi. Winter fog campaign WIFEX 2023-24 was successfully conducted. A state-of-the-art aerosol lab was set up at IMD headquarters as part of WIFEX 23-24. WIFEX experiment was expanded to Jiwar Airport in Noida. A 21-member ensemble for fog forecasting has been set up to provide more reliable forecasts. Under the Atmanirbhar Mahabharat initiative, K-band radar has been revived in August 2024 by IITM in-house radar team of the Atmospheric Research Testbed in Central India, with the help of the OEM from USA and Indian industry at the Bhopal site. Following the recommendations of the IITM Research Advisory Committee, a brainstorming meeting was conducted to develop a tropical meteorology program, biometeorology program of national importance. IITM is preparing a concept report for this important program. IITM organized several seminars and events, national and international workshops and conferences during the last year, including the Professor Ananthakrishnan Colloquium, the India Meteorological Society Pune Chapter's annual Monsoon Workshop and National Symposium, and activities under Mission Life. The 9th International Day of Yoga was celebrated, sessions for Wakaris of the Pandharpur Yatra, among others. Various activities were undertaken for the promotion of Raj Bhasha, including the Vishwa Hindi Divas 2024 competitions, and the National Joint Raj Bhasha Scientific Seminar in 2024 was jointly organized by Agakar Research Institute, the CSIR National Chemical Laboratory, National Center for Cell Science, and IITM. Several scientists have brought laurels and honors to our institute for their outstanding performance and achievements. In particular, Dr. Roxy Matthew Cole was awarded the prestigious Rashtriya Vigyan Puraskar, the Vigyan Yuva Shanti Swarup Bhatnagar Award for the year 2024 in Earth Science. So these were some of the few important scientific research outcomes and accomplishments over the past year. Good day to all of you. Thank you.
Thank you, sir, for briefing us on IITM activities. We will now begin with the addresses from our dignitaries. I kindly request all our distinguished guests to take their seats in the VIP row downstairs. Thank you.
Yes, sir.
Professor Berrien Moore.
Yes, sir. We'll take care, sir.
Yes. Thank you. May I now request Dr. Ayantika Dey, Senior Scientist at IITM Pune, to provide an introduction of our chief guest, Professor Berrien Moore. Following this, we will have the privilege of hearing the IITM Day lecture.
Today, Today, it is my distinct honor to introduce a truly remarkable individual who has made profound contributions to both science and society. Our chief guest for this Foundation Day celebration, Professor Berrien Moore, is a renowned earth scientist whose career has been defined by groundbreaking research, visionary leadership, and a deep commitment to understanding the planet's most pressing challenges. Professor Moore started his career as a mathematician. He received his Bachelor of Science in Mathematics from the University of North Carolina and his PhD from the University of Virginia in 1969. However, he declined a Fulbright Fellowship in Mathematics to begin his journey into earth sciences. via a fellowship from the Woods Hole Oceanographic Institution. Following Woods Hole, Professor Moore began his scientific work on the global carbon cycle using innovative mathematical models to probe both terrestrial and oceanic systems. During the late 1980s and the 90s, as chair of NASA's Space and Earth Science Advisory Committee, he oversaw key missions, including the launch of the Hubble Space Telescope and approval of the Earth Observing System. In recognition of his leadership, he was awarded NASA's highest civilian honor, the NASA Distinguished Public Service Medal. Dr. Moore was also honored by NOAA with the Administrator's Special Recognition Award and the Dryden Lecturership Research Medal of the American Institute of Aeronautics and Astronautics. Dr. Moore chaired the scientific committee of the IGBP and is one of the architects of the Amsterdam Declaration on Global Change. As a coordinating lead author of the third IPCC assessment report, he has been honored for contributing to the award of the 2007 Nobel Peace Prize. Professor Moore started his academic career at the University of New Hampshire and also served as the director of the Institute for the Study of Earth, Oceans, and Space at UNH. In 2008, he became the founding executive director of Climate Central, a think tank dedicated to provide objective information on climate change. Currently, Professor Moore holds the Chesapeake Energy Corporation Chair in Climate Studies at the University of Oklahoma, where he also serves as Dean of the College of Atmospheric and Geographic Sciences and Director of the National Weather Center. He has published extensively in the global carbon cycle, biogeochemistry, remote sensing, environmental and space policy. Professor Moore is the architect and principal investigator of the Geostationary Carbon Cycle Observatory, GeoCarb mission, an initiative to provide critical data on the Earth's carbon cycle and vegetation health. Ladies and gentlemen, it is my honor to welcome here Professor Berrien Moore to deliver the IITM Foundation Day lecture on the GeoCarb mission. Sir, please.
Sir, do you want to use mic or this one? I'll use this. Use this. Okay, sir. Okay, sir. Yes, sir. This one, sir.
In slideshow.
Yeah. Wait, sir. 1 minute, sir. This is which one? This will go on. So there's a button. Slide forward. Okay. This will go slide forward, slide backward. You can test that once. This one.
Yeah, yes. Here.
Yeah, press once. It is not going forward.
I don't want to move it forward yet. Okay?
It is going forward.
I'll try.
It's going? It is going, sir?
Let's try.
Yeah, it's going. So, please.
Well, thank you. I've changed the title a little bit to focus, to make sure that we all understand the challenge that we face with climate change. For it's in that context that the GeoCarb mission makes an important contribution. But we need to understand the really profound challenge that human society faces regarding climate change. I'm deeply honored to be here. I think that this scientific village, as we heard so clearly, is central for the planet to address the kinds of questions that I'm going to be discussing. This, I'm sure, is familiar to everyone in this audience. It's the remarkable record established by David Keeling at Mauna Loa, the second highest mountain on the big island of Hawaii measures the concentration of CO2 beginning in IGY, the International Geophysical Year, which was the same year in which Sputnik was launched. In some ways, I think the Keeling record is even more important. You see two things in this record, in the concentration of CO2 in the atmosphere. And that is, you see the industrial metabolic system, the industrial pressure on the carbon cycle, as you see the steady increase upward, so that we're now somewhere above 424 parts per million, up from about 317 in 1958-59. The other thing that is quite remarkable in this record, and it's even more visible in this, is you see the planet's metabolic system. The drawdown of CO2 in the growing season, the spring and summer. And then the upward trajectory of CO2 as that drawdown by the biosphere stops in the fall and winter. So you see the annual cycle of the Northern Hemisphere in the Keeling record, as well as the industrial metabolic system. When I began working on this problem, and in fact, I was honored that Bert Bolin and I wrote a paper, but it just turns out the paper's wrong. And that is, we were very convinced that the terrestrial biosphere really played no significant role on the net exchange of CO2. Yes, it plays a very significant role in what we just saw on the Keeling record. But in terms of a net uptake of the fossil fuel CO2 perturbation, the terrestrial biosphere was relatively neutral. That as you put CO2 in the atmosphere, about half went in the ocean. Except as we read mathematical model after mathematical model, we never could get the ocean to take up that much CO2. Later, as we started looking very closely at the Keeling record, we saw that year-to-year variations were not explained by the year-to-year variations in the perturbation of the fossil fuel contribution. And they were not explained, those year-to-year variations were not explained by the ocean uptake. So all of a sudden now that the only explanation was that the terrestrial biosphere was exchanging net carbon at different amounts each year. Now, as we've looked at it more carefully, we actually see that the terrestrial biosphere takes up about 30+%. The oceans take up 26%, and the 44% builds up in the atmosphere, 47 in this case. This is a very different dynamic than we thought about in the 1980s, where we thought it was really an atmosphere-ocean system. Now, as we look at this, we also have to think about how constant are these relationships. As you put CO2 into seawater, there's a dissociation and pH drops, so-called acid acidification. As the pH drops, the solubility of CO2 drops. As the skin surface temperature, as the sea surface temperature increases, solubility declines. So the more you look at this record in terms of the ocean-atmosphere exchange, one sees a repeated signal of positive feedback loops that could be changing this record in the future. In the terrestrial biosphere, it's not as clear. But one thing that does appear is that during El Nino, the terrestrial biosphere takes up much less CO2, and in fact could actually be a source. The concern with this is that many of the climate models show that we move towards more El Nino-like conditions in a climate change. So that means that some of these positive feedbacks would simply imply that more CO2 in the perturbation stays in the atmosphere. What's fascinating is if you look at the historic record by looking at ice cores of the concentration of CO2 in the atmosphere, you actually see one of these feedback loops operating looking carefully at the period of the 16th and 17th centuries during the so-called Little Ice Age, you see a cooling of the oceans and a decrease of CO2 in the atmosphere. Then, of course, the Industrial Revolution comes, and you begin to see what we're faced with today. And this record of the ice core runs directly into the Mauna Loa record. If you look at methane, you're seeing some of the same problems, the same characteristics, namely the perturbation of the Industrial Revolution on the concentration of methane in the atmosphere. What's very important about methane is that it's a very strong greenhouse gas. The thing that causes methane, shall we say, to be in second place with respect to the perturbation of greenhouse gases is that methane is a relatively short-lived gas in the atmosphere, roughly 9 years. Even though molecule for molecule, it's a much stronger greenhouse gas than CO2. So depending upon what type of time horizon, so in this case, the graphic shows that methane is 28 times stronger in terms of the greenhouse warming potential if you look at a 100-year time scale. If you look at, say, a 25-year time scale, it's something like 84 times the CO2 signal. The other thing that's important to realize about methane is that the number of sources are relatively few by comparison to CO2. But before I turn to that, there's also something about methane that we really don't understand. And that is what happened in the late 90s and into around 2010, where the concentration of methane stopped growing in the atmosphere. I mean, it could not have been that the source terms weakened. That's just not likely. So there's had to be something in terms of the sink term, namely the OH radical and its impact upon methane, that somehow slowed. It shows up even more if you look at the bar chart of, say, the annual increases. I mean, something very distinctly happened that decreased. In fact, methane even dropped in the atmosphere. This is a really profound question. What was going on? You certainly don't see that now because now you see the upward trend. This is where I was at a few moments ago, just mentioning methane is that there's several reasons I think that methane is something that we ought to be thinking very seriously about attacking. And that is the number of sources. The two main sources in terms of the perturbation problem are really fossil fuels, the production and distribution of fossil fuels, and leakage of methane into the system, and the agro ecosystems where you have material that is decomposing in an anaerobic environment or in landfills. So in some ways, you have two targets in terms of source terms that we could think about how do we really attack that. That's very different from CO2. CO2 is occurring any time that there's fire. And humans love fire. And so the number of sources for CO2 is just extraordinarily immense. Anytime something is being burned, whether it's in an automobile or a power plant or a barbecue, CO2 is being formed. So I think methane in some ways is, and I'll come back to it, it is the low-hanging fruit in terms of what is it that we can do? What can we do now? And I think the fugitive methane at gas lines and fossil fuel production areas is something that we could be attacking. We could also think about landfills. Perhaps we could mine the methane out of the landfills and use it as a fuel. So here we are. So let's just be very clear about facts. Carbon dioxide and methane are greenhouse gases. Since 1750, or essentially since the Industrial Revolution, their concentrations have changed. CO2 has increased 50% in the atmosphere. Methane has nearly tripled in the atmosphere. The increases are due to fossil fuel burning and a secondary agricultural and animal husbandry. Carbon dioxide is a very long-lived gas, therefore stabilization of the concentration of carbon dioxide in the atmosphere is going to be very difficult. And there's also this positive feedback loop challenge. Methane is chemically active and hence short lifetimes, but it's a very strong greenhouse gas. But as I tried to point out, I do think that attacking the sources of methane is the low-hanging fruit. And this is something that we should agree as a society that we will make this attack on the methane problem. I think that's extremely important because CO2 is almost frustrating sometimes when you start looking at what is it that we can do to stabilize the concentration in the atmosphere, not stabilize the emissions. Stabilizing the emissions does not lead to a stabilization in the atmosphere. Methane is something that we should be attacking. The other aspect of CO2 is that it does directly relate to industrial society. And that has been the characterization of essentially every economic system on the planet. There's a production of CO2 from energy production. We often hear, well, climate changes. We've had climate change. Weather changes, climate changes. This is a very different form of change. It's a change that is happening rapidly. It leads to an intensification of the hydrologic cycle. More water is evaporated, more water will come down. I think most importantly, it's a change that humans have induced. It's not due to orbital dynamics. It's something that it is a perturbation from human society. As I noted, CO2, to stabilize the concentration is extremely difficult. And that means that we really need to begin to think very seriously about mitigation. How can we make cities more sustainable in the face of climate change? How do we make all societal institutions more sustainable? Yes, we should continue to work on this rate of change in terms of the perturbation, and methane is the low-hanging fruit. But let us not underestimate how challenging this is. And finally, we have to take that science must be our guide. Okay, one thing I want to just single out in this slide, and that is the fourth bullet. We have to be very careful about what I would call feel-good strategies, things that make us feel like we're doing something good, but really may not make any sense. Everyone is very excited about electric cars. Yes, electric cars, we're not burning gasoline. We're not contributing CO2. But be careful what you plug your electric car into. So plugging your electric car into a coal-fired power plant is not a good idea. So I think we really have to think very creatively about what it is that really makes sense and that is doable. The other thing I think in the classroom, that we all participate in these discussions, we have to be very careful about giving a sense of helplessness, that there's nothing we could do. Yes, climate, if we stop putting greenhouse gases in the atmosphere today, climate would continue to change. The ripples in the system have already been unleashed. So that it's already baked in, but that does not mean that as we discuss this around the dinner table or discuss this in the classroom, we must avoid any kind of sense of helplessness. And I think there's a danger there that I've seen in the classroom. The other thing is we have to think of this as a systems problem. We have to think of this as a system of systems problem. It's a problem of problems of problems. There's a cascading nature, and that we have to think very carefully about as we suggest solutions, electric cars, that we are really suggesting something that makes sense in this systems level discussion. I think there's also something that has always bothered me. We said, well, let's make our society sustainable to surprises. And, well, yes, but if a surprise is really a surprise, it's hard to make our societies, resistant to, or, that we can accommodate surprises if I don't know what the surprise is. But there are ways of thinking about this in terms of just how sustainable is our activity. And let's think about sustainability not over weekly timescales, but over the long haul. I touched upon this, but I really think that this is a very important thing. And that is, as we ought to begin to think perhaps that natural gas is a good bridge fuel. We ought to replace every coal-fired power plant every coal-fired power plant should be replaced by natural gas. The BTU CO2 ratio, coal is just not good. So you can cut your emissions just by simply switching the fuels. But then we need to be very careful that as we switch to natural gas, that the fugitive methane is no longer there, that we have caught the fugitive. Okay, now I'd like to switch to geocarbon. In 2010, at the American Meteorological Society meeting, I had an idea which I really could not get anyone to listen to, other than my late mother-in-law, because I grew up in Atlanta and my late wife were from Atlanta. I was staying at night with my in-laws and my wife at her home, and I kept telling them about this great idea I had about a geostationary spacecraft. And the idea really came from the Orbiting Carbon Observatory out of JPL. OCO2 is listed as OCO2 because the first one did not make it to space. It went into the ocean. And so OCO2 was launched and is operating still, but it has an extremely narrow swath width, about 10 kilometers. So a very narrow swath, and then you realize how large the atmosphere is, and this 10-kilometer swath, but it was making marvelous measurements in that swath. So I kept thinking, is there some way that we could take that narrow swath, but instead of the swath repeating 1,500 kilometers the next time around the planet, and then another 1,500 kilometers, always being way separated, these swaths, is there some way to take a swath and move it over? Well, you're not going to do that in low Earth orbit. So that led to the idea of going to geostationary and then putting a slit in the optical train such that that slit would be like the OCO swath. In our case, it was about 6 to 7 kilometers wide and 2,200 kilometers north-south. So now we have a swath, a 2,200 kilometer north-south, 6 to 6.5 kilometers wide. I then break up that 2,200 kilometers into 6 to 7 kilometer buckets. So now I have an OCO-like mission for that 2,200 kilometers, and I stare for 9 seconds. And in 9 seconds, I get the signal to noise that OCO has in low Earth orbit. Then I move the slit over and stare for 9 seconds and move the slit over. This will give you a feeling for this. This is speeded up. There's geocarbon geostationary orbit, and OCO is down below in polar orbit. To give you a sense of how much it's speeded up, that takes about 90 minutes for OCO to go around the planet. And so this moving the slit over is going much, much faster than normal. You can kind of get a gauge by OCO going by. That takes 90 minutes. So it takes about 2 hours and 15 minutes to sweep out the 48 states. For Brazil, it takes about an hour and 45 minutes. But during sunlit conditions, what we're measuring is the reflected light off the surface. And we're looking down, as I'll see in a moment, in 4 channels. 2 for CO2, 1 for methane and CO, and 1 for oxygen, which I'll come to in a moment. So now this will give you those swaths of OCO. Those are actually larger than reality. A 10-kilometer swath wouldn't even show up here. But now this is giving you a feeling of the OCO. These are all 10-kilometer grids. We're at about 6.5 kilometer, but we just mapped it out at 10 kilometers. And so now you're looking at this highly variable field, but you're mapping CO2 and methane rather than just sampling the atmosphere. So that was the idea of geocarb. The other thing is that we wanted a concentration. So with our characterization of CO2 and methane, we're really getting the total column in that 6 kilometer by 6 kilometer tube, if you will. I'm getting the total amount of CO2, total amount of methane. But I also measure the total amount of oxygen. And so the total amount of oxygen, then that gives me a way to get to concentration. Total oxygen divided into total CO2. Total oxygen divided into total methane. What's interesting is that in that oxygen channel, which we'll see in just a moment, you actually see also the solar-induced fluorescence, which gives you a measure of photosynthetic activity of vegetation. And that in itself, I think, is a great contribution of geocarb. So this graphic here gives you somewhat of a sense of the difference between OCO and geocarb. Now, OCO is a fundamentally, it was where all of the ideas for geocarb came from. We use essentially the same channels. We add methane. So one can think of geocarb as OCO in geostationary orbit. But this gives you a sense of the undeterminedness that you have faced in LEO. The green bands, the first green band on the left, this is Mexico City that we're looking at. The first green band is the first passage of OCO through Mexico City. 7 days later, you see the next green band. And then 7 days later, you would have the first green band. So you get a return every 14, 15 days. But it'd be very hard to characterize the CO2 emissions or methane emissions from Mexico City with that strategy. Whereas geocarb is the checkerboard that you see. And that checkerboard could be every day. Every day. So the goal of the geocarb mission is to produce a fundamental transformation of our understanding of the carbon cycle, particularly our understanding of the terrestrial sink. It also demonstrates a technology that one could use for treaty verification, at least over the Western Hemisphere. So here's the instrument. It weighs about 157 kilos. It roughly is a meter by 2/3 of a meter. It sits as the left-hand picture. There it is. It sits, shall we say, upside down on the bottom of a geostationary spacecraft. Light is collected through a telescope. And then we use a grading spectrometer in 4 wavelengths, which are described there. The first is the oxygen A band, then the 2 CO2 bands, and then the methane channel, all in the near infrared. When I first thought about geocarb, I thought, well, we could put this instrument anywhere. And 3, shall we say, geostationary slots showed up. And the one on the far right is the slot that we chose for geocarb, roughly 90 degrees west. But one could put it over 110 east, or one could put it like at 70 east over the Indian Ocean. And these would be the domains. These would be the scanned boxes that you could apply geocarb to. This is a private wish of mine. One more geocarb would be wonderful, and that would be to put it at 70 east. And then perhaps one could find another nation state to put one at 110 east. Here were our scientific questions that geocarb was to answer, and the first was to get a real understanding of what is the anthropogenic source term and how does that compare with the anthropogenic or the terrestrial uptake in forests over the Western Hemisphere, or the source terms over the Western Hemisphere from terrestrial systems. The other is, for instance, let's look at Amazonia. There is a signal of methane coming off of Amazon. European flight showed this. And I think what we now understand what happens is that during very heavy rainfall, there's very little methane coming out because everything is flooded. And if you're in a drought, then there's very little methane coming out because you're not in an anaerobic situation, you're in an oxidation situation. But there's a point in between where the tropical forests seem to be a very large source for methane. We don't understand that. It's a hard one because of the cloud cover. And then finally, look at methane sources over CONUS, over the continental United States, and particularly look for fugitive methane. Remember, we could be mapping the United States every day, or perhaps twice a day, or 4 times a day, or maybe once a week you change it and you just map the agricultural and fossil fuel regions of the United States. Because you can change those scan boxes to fit whatever you need. Now, the challenge for geocarb, and the very real technical challenge, is that you want to make these concentration measurements, total column concentration of CO2, you want very high precision. You really want to be measuring things at 99.7. So very, very small error bars. And the reason for that is because error in the concentration measurement then would get that error, not knowing that error, taking it as truth, then you're going to infer different sources and sinks. So your concentration measurements in the atmosphere are there because what we want to do is to get to the sources and sinks at the Earth's surface. So all of the information is in the gradient of CO2 concentration and in the gradient of methane. We use CO as kind of a way of tracking. Is that an anthropogenic burning for CO2, or is it coming from oxidation? And the CO will give you that signal. So this is just really trying to pull out 2 of the important characteristics, is that it's a very precise measurement that we're making from geostationary. And that's extremely important in terms of, as I just described, about the gradient. And it is a persistent measurement every day, or multiple times a day, depending upon what your scan strategy is. We have one that we call the I-35, that is the interstate highway in North America that essentially connects Houston to Minneapolis. And we could even have a scan strategy that says, go 1,000 kilometers east of I-35 and 1,000 kilometers west to I-35, that's roughly the Rocky Mountains. You can scan that 16 times in a day. So if you're, for instance, looking at the solar-induced fluorescence, or if you're looking for fugitive methane, this could be a very important strategy. The other, I think, important character is geocarb is proactive. You can change your scan. LEO, if you're in LEO orbit, yes, OCO can point some, but you're pretty well fixed as to where you're going to be, when you're going to be. Whereas geocarb, you can change that. You can start early in the morning in Brazil, scan there, then move up to North America, just scan the middle of North, and then go back to South America, all in one day. And it's wall-to-wall. That gets at this inversion problem, because if you're trying to take concentrations in the atmosphere and invert those to fluxes at the Earth's surface, if you're dealing with a very sparse measurement set, you are underdetermined in that inversion problem. Whereas geocarb, you're almost overdetermined. Finally, on the SIF, I think that really, I think that the solar-induced fluorescence may in some ways have a unique value in terms of allowing us to pull apart gross primary production from net primary production, which has been a great challenge to biologists. Okay, now let me go on to some pictures and share with you the instrument. This gives you a picture of the telescope, which is shown there with the lid closed. We were just about to go into thermovacuum, and the lid was closed. And so I immediately made sure that everyone knew that lid needed to be open if we were going to make measurements in thermovac, which we did. The two large upward pointing objects are star trackers, so that we know precisely where we are at all times. And the spectrometer is down below, as you can see in the following graph I'll go back to. This kind of gives you a sense of where the spectrograph is and the telescope. So the left-hand picture looks upside down, but that is actually the configuration in which CO2 would be, geocarb would be flying. This has not been an easy journey. And in fact, on November of 22, I received a phone call from NASA headquarters, and it was an interesting time. We were going to a celebration for the Dean of Fine Arts at the University of Oklahoma, and it was a black tie celebration. I was trying to remember how to tie a bow tie, and I was struggling trying to remember how to tie a bow tie when I got a phone call. My wife said, well, it's NASA calling, and I thought, 7 o'clock at night? Not going to be good news. And it was that they were going to cancel the mission, that they had determined that with the remaining funds, we just couldn't complete the instrument. And so, but they were gracious enough to not take the funds away from me, and they said, you can try, but it's our determination this is not going to be possible. And we also don't have a spacecraft to put you on. Well, that was in November, and in late August, roughly 9 months later, we actually were able to complete the instrument. This is Sean Crow, my deputy, with the instrument, and we are in the process of, at that time, moving the instrument to this location, a big thermovac chamber. And it's quite interesting to see the little geocarb instrument, even though it's 157 kilos, this is a thermovac chamber that is really meant to have an entire spacecraft. So geocarb gets lost a bit in the chamber, and yet this turned out to be a very important time for us. We were in the chamber from September of last year to September to October. We were there for about 27 days, operated at a variety of temperatures. We actually were able to bring light in through a window in the roof, and so geocarbon could actually look at the atmosphere, and we could demonstrate that we could make CO2 measurements in the atmosphere. This turned out to provide us with roughly 60,000 data records, and for the last 9 months, we've been analyzing those data records and presenting them every month to NASA headquarters. And we identified 2 or 3 tall poles, as we would say, things that we needed to register. One was dealing with a certain geometric distortion in the data. And so we now have a contract with NASA grant to work through these 2 or 3 remaining tall poles. And we hope by the end of summer in the next year that we can move into what's called characterization and calibration, where we characterize on the four detectors for each of the 4 wavelengths, that we characterize every pixel on those detectors in terms of their offset with respect to the radiation in that particular spectral band. So that characterization calibration program is out in front of us, probably to start late summer and into the fall of next year. And we're working with a plan right now to get to orbit in 26, hopefully before June. So this was the final instrument. ready for packing, which we did. And I decided, because it was just in the holiday season, that we should have geocarb packed up and a little Christmas wrapping added to it for NASA headquarters to receive their child that they had said couldn't be done. And there we are on the final meeting of the review by NASA headquarters and NASA Langley of the geocarb mission. And I treasure this photograph because we were with a commercial photographer, and with commercial photography, I know you've all had your pictures taken this way. They tell you to do certain things, and you do them because they are really in control of the situation. And so they told Lockheed and NASA to all look slightly towards me in the middle and to do this. And I'm sure the NASA scientists later thought, uh-oh, I probably shouldn't have done this. But we did. And so we hope to be in orbit in 26. Thank you very much for the honor of being here today.
Thank you so much, sir, for the enlightening lecture on climate change. Your insights have greatly enhanced our understanding of this crucial field. We can take up a couple of questions.
Before anyone wants to ask a question, I need to tell you that on my flight here, my hearing aid stopped working. However, there's enormous resources in Pune around the Institute for Tropical Meteorology. So at 8 o'clock last night, 8 o'clock in the evening last night, my hearing aid was repaired, so I'm prepared to take questions.
Hello. Sir, as you have shown, CO2 and CH4 trend is increasing. Ultimately, temperature is increasing. Many scientists, what they said, world leaders have delayed on making the decision on climate change. So in coming COP, what I want to say, it will be difficult to limit the temperature 1.5 degree. They are saying, regardless with any international treaty. So would you like to say something? Can you say something on this issue, please? Are you agree with them?
Well, yes and no. Let me see if I can put your statement into a little bit different context of maybe even asking what's the real value of measuring sources and sinks, these terrestrial systems? What's the real value given the fact that we've indicated how difficult it is to stabilize CO2 in the atmosphere? One could think about a strategy for the planet that said, can we manage the terrestrial biosphere in ways that actually, assuming that we can reduce some of the CO2 flux to the atmosphere from fossil fuel burning, can we manage the biosphere in ways that slow or maybe even stabilizes CO2? Could we, for instance, have farmers in a way grow carbon? And for instance, carbon could be stored in soils. Is there a way to, and you would actually increase the water holding capability? Our problem is we don't have the kind of measurements that tell us, point measurements. The terrestrial biosphere is so large, a point measurement is extremely difficult. The so-called bottom-up calculations are extremely difficult to really carry out with any confidence. So it's only when you begin to look top down that you can begin to think of strategies that might say, are there strategies of both reducing the fossil fuel carbon, but also increasing sink terms in the terrestrial biosphere? That's really what we've been trying to think about. The fugitive methane, to me, geocarbon is ideal for that because it'll tell us exactly what 6 kilometer by 6 kilometer pixel is that methane coming from. And then we can go in with strategies for really localizing that down to, well, it's at this place the system is leaking. I'm not sure that really addresses totally your question. Comment?
Yeah.
Yes.
Good morning, sir. I think we have learned a lot from your talk, and I heard your previous lectures many times online, and then I was really wanted to meet you. So I'm Yogesh Tiwari. I'm leading Greenhouse Gases Observation Network here in IITM. So we started CO2, CH4 measurement since 2009. In India now we have close to 9 to 10 sites where we are working. So my question is, generally as per WMO scale, we are achieving 0.1 ppm of accuracy in our surface observations, which is really required for the top-down modeling.
Right.
Yeah. So whether GeoCarb provides this accuracy so that data can be utilized in the inverse modeling? This is number one. And number two, do you think in the future these satellites observation will replace the surface observations because you have more coverage at those locations where we do not have surface observations?
I want to be very clear. The point measurements at various facilities of surface measurements are extremely valuable, particularly for validating and verifying the observations from the top down from space, whether it's LEO or GEO. Extremely valuable. The so-called TCON network is extremely valuable. It's being used today for OCO and the GOSAT from Japan and others. The CO2M mission coming out of ESA. These will be extremely valuable, but I still think it's the top down that is going to tell us about these fundamental questions about sources and sinks of CO2. Now realize that for GeoCarb, wherever we fly it, in geostationary orbit, it's only measuring sources and it's measuring concentrations over the terrestrial landscape. There's not enough reflected light off the surface of the ocean in terms of making an you could measure ocean color, but we're not looking at an imager. We're trying to making a concentration in the atmosphere measurement. So the light coming off of the ocean, unless you're able to look at the glint spot, is insufficient for geostation, particularly for geostationary. However, most of the sources and some of the sinks are terrestrial. And so by looking at the source regions, which are terrestrial, I think GeoCarb, and particularly if we could fly it in the two other slots, one at 110 east and one at 70 east, that you would then have, just as we do with weather, you have geostationary satellites and you have LEO satellites for weather. Geostationary are very valuable. For instance, the lightning mapper, and we saw some of that electrification discussed earlier. The geostationaries are very, very powerful for, shall we say, forecasting weather within the next hour. Whereas the LEO bus may be on the other side of the planet. Now, LEO is very good feeding numerical weather prediction models because you need global data. But the GEOs have a role, and I think the same would be true for what I believe is necessary is an operational carbon observing system, because this is something that we're going to be faced with for the next 100 years.
Thank you so much,
Thank you
sir.
very much. Thank you very much. I'm honored to be here.
To take your seat.
Thank you.
Thank you so much. Now let us move forward.
अभी वक्त है एक छोटे अल्प विराम का। इसके बाद हमारा दूसरा वैज्ञानिक सत्र और श्रेष्ठ योग्यता प्रमाण पत्र व सम्मान चिन्ह कार्यक्रम 12:15 से 1:30 तक आयोजित किया जाएगा। आप सभी से अनुरोध है कि अपना स्थान 12:15 पर यहाँ अवश्य ग्रहण कर लें। इससे हमें अपना वैज्ञानिक सत्र प्रारंभ करने में सहायता मिलेगी। अब हम आप सभी लोगों को विशिष्ट जलपान के लिए आमंत्रित करते हैं। जलपान की व्यवस्था मेघदूत के बेसमेंट में की गई है, इसी हॉल के। धन्यवाद।
Before we resume with the next session, we warmly invite all of you to join us for high tea in the basement of Meghdoot Hall. Our esteemed dignitaries will be served high tea in the reception area. I kindly request everyone to reassemble here by 12:15 p.m. Thank you. किसका पेन था? आपका पेन?
ये मुझे पता नहीं, ये मैंने किसी से उधार लिया था।
हाँ, ये भी मैंने किसी से लिया। अब नेक्स्ट सेशन क्या होगा?
आपका हुआ है क्या?
क्या
इधर का हो गया?
हाँ, हो गया।
हेलो, सभी लोग अपना स्थान ग्रहण करें। अब हम
May I request everyone to please take your seats?
नमस्कार। अब हम अगला सत्र आरंभ करने जा रहे हैं। आप सभी लोगों का पुनः इस हॉल में स्वागत है।
Welcome back, everyone. May I now request Dr. Leena, Senior Scientist at IITM Pune, to provide a brief introduction of our guest of honor, Professor S. Anand Krishnan. Following this, we'll have the privilege of hearing the IITM Foundation Day lecture. Thank you.
Okay. Good afternoon, everyone. It is my distinct pleasure and honor to introduce to you Professor S. Ananthakrishnan, Indian National Science Academy Senior Scientist and Adjunct Professor in Savitribai Phule Pune University and former Director of Giant Meter Wave Radio Telescope. An internationally and nationally known radio astronomer, radio scientist, Professor Ananthakrishnan had a brilliant academic career and got his BSc Honours, BTech and MTech degrees from Calcutta University and later his PhD from Tata Institute of Fundamental Research and University of Bombay in 1976. He was a J.C. Bose National Science Talent Scholar during 1961 to 66 and an academic member of TIFR, Mumbai for 41 years and was involved in commissioning and operation of two major radio astronomy facilities known as Ooty Radio Telescope in 1970 and Giant Meter Wave Radio Telescope at Narayangaon in 1999. He commissioned GMRT in 2001 and was its Observatory Director till 2004 and retired from TIFR as Senior Professor in 2007. Since then, he is an Adjunct Professor in the Electronic Science Department of Pune University. He taught the MSc students of Electronic Science Departments Antenna, Electromagnetics and Communication Systems from 2007 to 2019. During this period, he was also involved as chairman and member of numerous major national projects like AstroSat, 3.6 meter optical telescope, 21 meter MSE gamma ray telescope, 32 meter Belelu radio antenna, etc. He is an elected fellow of all the national science academies and has won many awards such as INSA International Vainu Bapu Award, Professor S.K. Joshi Memorial Award, C.V. Raman Gold Medal, as well as other national, international fellowships. Professor Ananthakrishnan was the chairman of ISRO Pune University Project Evaluation Committee for past 12 years and also a visiting scientist in various organizations all over the world. Without further ado, please join me in welcoming Professor S. Ananthakrishnan to the stage for delivering our Foundation Day lecture on the topic Exploration of the Earth, Moon, Space and Beyond through a New Low Frequency Window. Welcome, sir.
Thank you very much. Thank you very much. No, this should be okay. Yeah, only my throat is not in good shape. I think if I have to only look at this, then maybe it's easier. Yeah. Okay. Can you put the whole thing?
मैं आप सभी लोगों से अनुरोध करता हूं, कार्यक्रम के बीच कृपया जिनको सम्मान चिन्ह मिलने वाला है वो बाएं साइड अर्थात लेफ्ट साइड बैठ जाए।
Okay.
कार्यक्रम स्टार्ट करते हैं। So this will go forward, this will go backward.
Okay. Okay. Thank you. Thank you.
Just check something. Is it working?
No. Okay. Yeah. Thank you very much. It's a great privilege that I am here today. Although my throat is not in a good shape over the last few days because of a throat infection. Kindly pardon me for that. It's a great pleasure and privilege to be addressing a set of very distinguished scientists here, including my Vice Chancellor, Professor Gosavi, Professor Moore, and Professor Venkatesan, and Dr. Krishnan, and so many other friends whom I know. Dr. Kamra, of course, I've known him for many, many years. It has been my privilege to be associated with IITM for nearly 40 years because I knew Professor Pisharudi, then I knew Professor Ananthakrishnan, my own namesake, who has done yeoman's work here, and so many other people who have come since then, Professor Dimri and Professor Goswami and various others. And so I have been off and on coming to the Institute for various things, and I have also been very recently, thanks to Professor Dr. Krishnan, I have been involved in their new Doppler radar purchase. It's a project of great importance for cloud testing and Doppler weather radar. And therefore, I am very happy to be here today talking to you about a subject which may not be quite fitting to this audience. So I have a prologue. I may not be the appropriate person to be giving a Foundation Day lecture in an institute for tropical meteorology that deals with the solar radiation interaction with the dense tropical atmosphere. But as a solar radio astronomer and a radio scientist, I can see my myriad ways in which the sun's radiation interacts with not just the Earth's atmosphere, but the entire solar system extending to the limits of heliosphere. After all, we start from the Earth and we talk about troposphere, we talk about stratosphere, and then we talk about mesosphere, and then the exosphere, thermosphere, and exosphere, and then we are into deep space. And that is an area in which we are, of course, as an astronomer, I am very interested. And therefore, I will want to touch upon aspects of how the near-Earth moon space is impacted by radiation and how one can explore that. Because remember that, and offhand I am just saying, that Earth is an extremely, infinitely small object in relation to the cosmos. And we are very fortunate that we are living here on this planet and we are able to make a sense of all these things, and we are able to see the external world. and so on and so forth. And it's a very precious, precious life that we have, as Professor Moore very eloquently pointed out. And it is all depends upon very delicate balance between lives and non-life. And therefore, it is always worth exploring the outer aspects of the Earth. And the nearest that we can think of is the Earth-Moon space. And then the next, of course, is the Sun-Earth space. And of course, the Sun is the primary body which really shines on all the planets and has given rise to life forms on the Earth. So I will go back some years. Chandrayaan-1 for exploring the moon was being proposed by ISRO in the year 2005. And Professor N. Bhandari from Physical Research Laboratory requested me at that time to attend that meeting. He was very insistent. I was very hesitant, since I couldn't possibly contribute anything to it from a radio astronomy point of view, so I thought. But after hearing the discussion, I decided that understanding the near-Earth space from the moon via low radio frequencies is a very important topic and worth spending effort. And therefore, my interest in building a space payload at very low frequencies began. But just around the time I was retiring from my institute, the Tata Institute of Fundamental Research, so obviously the then Vice Chancellor of Pune University, Dr. Kolaskar, asked me, why don't you come here? Why are you going anywhere else? And so I ended up in Pune University, and I have been there ever since. And it's a great pleasure that Professor Gosavi is here. So my interest began in building a space payload. And let me begin with some preliminaries that are relevant here. Professor Moore explained about the observations using his OCO2, as well as, what was the other one? Geocarb, yes, Geocarb 2. But they're all, you are talking of well above the atmosphere. Now we are talking of atmospheric opacity here. The y-axis shows opacity and the x-axis shows wavelengths. And it covers the entire electromagnetic spectrum. And what Professor Moore was talking about was in the visible light range where most of the satellites operate. But then gamma rays and X-rays we do not observe from the Earth because the opacity is 100%. It just stops anything from coming in, and that's why we are alive. And then the visible is the next one, the longer wavelength. And then we have infrared, we have ultraviolet first, and then visible light, and then the infrared. And the infrared, there are some windows through which we can observe outside. But even then, it's much better to put satellites up there and all that. And then most of the rest of the spectrum is opaque again. And then suddenly, and that's why in the infrared region, NASA has launched a beautiful satellite, which is called the James Webb Space Telescope, and which is sitting at the Lagrangian point L1 and observing the cosmos and producing fantastic results. And then we have a suddenly opened window, a very large window, which is called the radio window. And the radio window has been more or less well studied now. And I will show you two major telescopes which we have built in India, of which I have been a very integral part of that. And then again, there is an opacity region, which is the very low frequency. And that's where I'll be talking today. And this low frequency region is important from many points of view, I'll tell you. But it is not very easy to observe from the ground. And so again, we need satellites. But then there are obstacles to do that. So the very low frequency, say less than 15 megahertz, which means about 20 meter in wavelength, long wavelength. So that is very relevant here, since significant interaction takes place between sun's rays and the exosphere. In this range, it is also the most difficult to explore, because we cannot do the observations from the ground, which would have made it much simpler. So it cannot be made from ground-based facilities because of the opaqueness of the atmosphere. It is not the ionosphere, but the upper part of the atmosphere, which is called the ionosphere. Now, briefly, ionosphere is created by the solar high-energy radiation, ionizing the atoms and molecules in the Earth's atmosphere, and that prevents any of these lethal rays from coming into the Earth normally. Atmosphere also cuts it off. Ionosphere also cuts it off. But in particular, at very low frequencies, in the diagram that I showed you just before, the low frequencies, the ionosphere acts like a mirror, double-sided mirror. It cuts off radio waves coming from the cosmic objects back and from the ground back. Now, this is what is being used by our AM broadcast people, so that you broadcast it, then the wave comes back again. And you can have vertical reflection. You can also have a hop reflection. It can go very far. As you go to very lower and lower frequencies, you can go very far and go through skip distances to even 2,000 kilometers, 3,000 kilometers. And that is a subject which is altogether very different. It is called the over-the-horizon radars, and which is used for surveillance purposes and all that. So this is a very interesting place to look at. And the long wavelength radiations themselves are not very easy to study, because they need correspondingly large antennas. You see, radio antennas transmit or receive optimally when the antenna length is half the wavelength. So if you have 20 meters wavelength, operating frequency, then you need a 10-meter antenna. Now this 10-meter antenna becomes quite large. As you can see, this is probably about 100 feet or so. And so about 1/3 of this is about 10 meter, something like that. So that is just one antenna, which is what is called an elementary dipole antenna. So, of course, you can also use monopoles, which is quarter wavelength. So it will be 5 meters only at 15 megahertz. So, but let us try to understand this a little bit more. This is where what is called the radio telescopes come. You are very familiar with the optical telescopes, because we see the moon, the Saturn, and Saturn's rings and Jupiter's moons and all that. Galileo discovered that the Jupiter's moons exist because of putting a small telescope. But remember, that is at optical frequencies. Optical frequencies means we are typically talking in terms of 500 nanometer. So at 500 nanometer, even your eye is big. So as a result, we can also see. And that is how you get about 10 arc-second accuracy when you are looking at people. So even far away, you can see two people walking, but not very much beyond. You will find that they merge into one. So similarly, in a radio telescope, the problem is that the wavelength itself has become very large. It is not nanometer. We are now talking in terms of meters, which is hugely different. Nanometer to meter is 10 to the power of 9 order. So you need correspondingly large antennas. And so a typical radio telescope, like what we have at Narayangam, which is about 80 kilometers from Pune, and which I recommend to all of you to just visit, just even as an excursion, because it is worth seeing. And I'll show you a picture of that. A simple antenna works in a very simple manner. You have a reflecting dish antenna, as it is one of a kind, reflecting dish, and it concentrates all the radio waves to a center, because it is a parabolic dish, so it comes to the focus. At the focus, we have a prime element, what is called a dipole. So the dipole receives the electric fields, converts that into current, and that is received by a simple amplifier and then a detector, and then you can go to the record, you can go to the computer, you can do whatever you like. So, but in the case of an optical telescope, even a 4-inch optical telescope, which is only about this much, that 4-inch optical telescope gives you an angular resolution of 1 arc second. If you calculate, because it is 500 nanometer divided by 4 centimeters or 10 centimeters, a 4-inch telescope. That gives you a huge advantage, and that is why Galileo was able to discover satellites of Jupiter. And we are discovering very many more things. But even an antenna, a single antenna of GMRT in Narayangam, which is 45 meters in diameter, at 1 meter wavelength, at 300 megahertz, gives you a resolution of about only 1 degree, which is 3,600 times worse than what you had, you know. So you need very large antennas at very low frequencies. Now, unfortunately, at very, very low frequencies, even these large antennas are not useful because the atmosphere itself is opaque. So there lies the problem. And so therefore we need to find some other way. This is one of the large radio telescopes built in India indigenously way back in 1970. I was just a graduate student. I joined this effort and I built a significant part of this telescope. And it still functions after 50 years. And this is the GMRT, which covers an area of about 30 kilometers and has 30 antennas, each of which is 45 meters in diameter, and which produces, therefore, if you do all this lambda by d mathematics, simple mathematics, you will get that it can produce even a second of arc accuracy at certain frequencies, and at certain other frequencies, it can produce as much as 10 arc seconds. So now, we go back to our subject. Over the past 2 decades, interest in solar and extrasolar astrophysical phenomena in the long wavelength range, that domain has triggered construction of many large meter wavelength radio astronomy facilities, like LOFAR in Netherlands, LWA, long wavelength array in the United States, MWA, Murchison Wide Field Antenna in Australia, besides ORT and GMRT. And there is a new telescope, of course, mother of all telescopes, which is coming up by 2028 or something like that, which is called the Square Kilometer Array, which was the original purpose of GMRT, but now that is coming in Australia and South Africa. But these facilities will not be able to conduct radio astronomy studies at ultra-long wavelengths, longer than 10 meters in wavelength. So the lateral spectral domain necessitates a dedicated radio facility above the ionosphere in a radio quiet place, and either shielded from man-made RFI sources or far enough from them to minimize its effect. But the ultra-long electromagnetic waves are a result of planetary emissions from outside and inside the solar system and of high-energy particle interactions. So exploring this band will create an image of our younger universe and uncover a lot of the so-called astronomical dark ages. You know, one of the holy grails of astronomy is to know how did the Big Bang take place. The original universe came into being. How did it come into being? How were the galaxies, how were the stars formed? How were the galaxies formed? And what are the secrets of the young universe? And how did, of course, finally, how did our own galaxy get created? And how did the Earth get created? And so on. So these are very fundamental questions concerning the Earth, Sun, interplanetary, interstellar medium, and the extragalactic universe, they may find answer in this wavelength range. Now, I'll take you back for a little while into an esoteric subject. On the left side is the Big Bang. And from the Big Bang, the universe starts evolving. Sorry. Can somebody help me? I think something went wrong. Yes, okay. Right, laptop is easier. Yeah, so this is the long wavelength science, very early universe. Low frequency waves carry a treasure trove of information about the first billion years or so of the universe's history. So in the initial stage, it's supposed that, we do not know really, suppose that there was a Big Bang, and from the Big Bang, the universe started expanding. There was only energy, and this energy slowly cooled, and that cooling took place over a period of years, millennia, and finally it settled down slowly. And then there was a time when it was all dark, and then suddenly it comes into light zone. And this is called the epoch of reionization. I will not go into the history of that. And then galaxies started getting produced, stars were forming, and then each star became a source of light and energy in itself. And this is how it just goes. Gentlemen, how does this work? I think this works from here. Yeah. Okay, in light of the above, we may say that the opening of a new spectral window for space in astronomical investigation does always result in major discoveries and could result in better understanding of not only our near space but also the far space environment. If we can place interferometric arrays or lunar-based arrays which consist of several antennas in tandem and combined together like what we have done in GMRT, then we can make them operation at 20 megahertz. It will cover a frequency range which is totally inaccessible today, or which is extremely difficult to observe from the ground due to ionospheric absorption and scattering. This is a region of electromagnetic spectrum which has sparse observation and is essentially unexplored so far. Therefore, it is worth exploring the electromagnetic environment near the Earth-Moon space at less than 15 megahertz or 20 meters in wavelength. So, the preliminary key objectives, scientific objectives are the investigation of electromagnetic properties of the lunar day-side plasma, the tenuous lunar wake with its turbulent boundaries, and the electromagnetic interactions between the Earth and the Moon, and the Earth's magnetotails, etc. I'll briefly again go off this and say that the Sun interacts with the Earth in a very, very strong manner. And this interaction is actually through magnetic fields. From the Sun, there is a continuous outflow of what is called the solar wind. And this is the exosphere of the Sun expanding continuously. And it is expanding at supersonic speeds, at 400 kilometers to 1,000 kilometers a second. Imagine, a wind is blowing from the Sun continuously, 24 hours of the day, millennia and billions of years. It's flowing. And this, of course, this gives rise to mass loss on the Sun, but which is really small. And this gives rise to what is called the solar wind. And this solar wind is so hot that it carries a magnetic field along with it because it becomes a plasma. At very high temperatures, matter becomes a plasma. And so this plasma embeds, magnetic field gets embedded into that from the Sun, and that comes and impinges on the Earth. And it is like banging on something, And then the earth takes a onion shape. So it has magnetically speaking, it has an onion shape. So it is not spherical anymore. It has a flat shape in the front where the magnetic field is hitting it, and it has a tail. And that is called the geomagnetic tail. And there is in the geomagnetic tail, the north field interacts with the south field, and therefore it creates an annihilation and creates disturbances and comes back again to the earth. And so around the earth, there are huge electric currents flowing all the time. They are called auroral electrojets, they are called equatorial electrojets, and so on. And as a result, the ionosphere gets created, and so on and so forth. The atmospheric interaction takes place, and so on. So these are the regions which we are trying to understand much better at these frequencies. So to get a thorough knowledge of this electromagnetic environment of the Earth-Moon space, this is a necessity before we can make sensitive low-frequency observations of the cosmos from the moon. So this is a long-term goal of all of us over the whole world. So we started thinking that what can we do sitting in the university environment, where of course I will mention this, in spite of Vice Chancellor being present here, that funding is very constrained and we are very fund-starved places. And so you have to think what to do. So we started with thinking that let us try to make a small space payload which will demonstrate that we can make observations. And then let us think of expanding that to antennas in space and on the moon even. So one day I envisage that we will have antenna arrays on the moon, just like on the Earth, and from which we can observe the outer space. Now, just to tell you the kind of rays which we are contending with here, this is again frequency in megahertz at very low frequencies, starting from about 0.01 hertz to about 100 hertz. Here. No, this is going from 100 up to 100 megahertz. So the lowest part of it is what? Up to the line. I think he has taken it away. The line, the vertical dashed line which you see there, that is 10 megahertz. Okay, that is the frequency space, the left side frequency space which we are talking about. And there we have all these things. At the top we have solar bursts which are coming in, and the Earth's own, what is called the auroral kilometric radiation is coming in, and then Earth's lightning is coming in. Then there is a cosmic background of the galaxy. The whole galaxy is emitting at frequencies all the way from very low radio frequencies to very high radio frequencies, and which is what led to discovering the galactic background finally. So the galactic background is there, and then there is emission from Jupiter, and there is Saturn, and Saturn lightning, and Uranus, and so on. So all these things are impinging, and we are surrounded by these radiations from space. And this is what we are trying to look at. But we have serious bottlenecks in doing this because there are many unknowns at this moment. And what is the radio frequency interference situation at this moment? What is the situation during day and night and seasons? And what is the impact of the ground propagation on the moon and on the RFI levels on the far side of the moon? These are issues which are of great importance. We have to understand this. I'll tell you a little bit about that. The human activity has become so omnipresent that you can see the Earth in radio waves from space. There is so much of radio waves which we are generating through our broadcast, through our wireless transmission, through various satellites, through radars, and so on. And human activities, other activities, automobiles, which are producing spark plugs, and which are producing sparks, fluorescent tubes, and so on and so forth. So there is tremendous amount of interference, which is radio frequency interference, which is stopping you from being able to see things. It is exactly like the light pollution which the astronomers are facing these days from the sky. For example, Elon Musk wants to put some 1,000 or 2,000 Starlink satellites. But the Starlink satellites disturb the night sky from any darkness. And I'm afraid that in about 100 years, from the Earth, you will not see anything. Anyway, from the Pune skies, you can hardly see the stars. You can see how much of pollution is there. I used to, when I came here to Pune, even in 2000, I could see the planet Mars from my house in Panchavati. And today I cannot see any planets at all, except probably Jupiter, once in a while when it shines very bright. So we are creating so much of pollution, and you can see the smog in Delhi, which IITM is investigating all the time, which is making it difficult for people even to see 2 meters, 3 meters in front of them. So we are creating pollution all over. It's not just light pollution. We are producing, of course, particles, 2.5 micron particles and all that, but we are also producing radio pollution. So this can be seen from the moon. You can see there, this is an orbiting satellite which is going around the moon, and when it is on the far side of the moon, when it is on the shadows of the Earth, suddenly the noise level falls. It becomes almost a straight line, as you can see. So shielding of terrestrial radio interference by the moon, as observed by the Radio Astronomy Explorer 2 satellite, even at a distance of 385,000 kilometers, which is the moon, close to the moon, the additional shielding by the moon provides only about 3 orders of magnitude of additional interference suppression. This is a very old observation. New observations are showing that it is much worse. The Sun-Earth L1 Lagrangian point at 1 million kilometers from the Earth is still seeing interference from the Earth at a very large amount. So this was our major problem in, first of all, to deal with. So the man-made RFI is very large, and it is something like 50 to 60 dB above the galactic background, which means it is about 1 lakh to 1 million times worse than even the galactic background, which is the basic background of the cosmos. So it is very difficult to see anything in this frequency range if the pollution levels are so high. But we must calibrate that too. Just like we are calibrating the CO2 and methane emission, we need to calibrate the low frequency interference. So at Savitribai Phule Pune University, during the past dozen or so years, we have been trying to train students to build a space electric and magnetic sensor, which is called the SEAMS-1, payload to be launched on a ISRO PSLV, a GSLV rocket to be sent to the moon, finally. Initially, we proposed this in 2010. We initiated a collaboration with Sweden and Poland, so to send such an antenna payload to the moon, but this was rejected by ISRO, saying that we need Atmanirbhar. So we were back to drawing board. And of course, the Chinese didn't believe in that, and so they have sent a Chang'e satellite to the moon. And so that is sitting there. And ISRO felt then that we need to develop our indigenous strength and demonstrate our ability to send any payload to space. But funding was very low. So in the first phase, after many years, we are ready to send an electric orthogonal monopole payload on a PS4 platform. Now, PS4 platform is quite interesting. This PS4 platform comes thanks to ISRO. After you have you launch a PSLV rocket, and so it sheds all the satellites, and then after that is done, it has only the engine remaining, the rocket remaining, and which is solar panels, and so it has nothing else, and it is destined to fall back into the atmosphere in due course. So all the energy, all the engine is cut off, and of course the solar panels get shut down. But there is an interregnum period between the satellites being sent and this falling onto the ground. That is of the order of maybe few weeks to few months. So ISRO has introduced a scheme whereby you can put a few payloads on the satellite, which will remain after the satellites have all been launched, and they will start functioning immediately after this is all done, and the rockets get shut down. So it is on its own momentum, and it is going around the Earth before slowly falling down into the atmosphere and getting burnt. So we decided that we will put our payload on this place, which is called the PS4 operational payload. So SEAMS-1 payload will be able to make observations for about a week, or maybe 2 weeks if you are very lucky. So this will be a proof of concept mission on a truly shoestring budget. The idea is to establish a baseline closer to the Earth by looking at our near-Earth environment at about 300 to 500 kilometers altitude. So we will be getting a baseline of the radio frequency interference at low frequencies in the frequency range 0.3 to 16 megahertz by mapping the radio frequency interference in low Earth orbit. We can possibly observe lightning, possibly observe auroral kilometric radiation and the Earth aurora, as well as maybe the sun, solar bursts and other things from the sun. And it will check the utility of the COTS components, the commercial off-the-shelf components in the low Earth orbit, and then show that it is a pathfinder for the complex phase 2. So the whole apparatus itself is fairly simple. We need an antenna deployment mechanism, but I will come to the antenna phase very soon. It's a funny antenna. It is a very small monopole. And then it goes through RF stages and goes through digital backend, usually through an FPGA, Vertex 5. And then it has electronic conditioners and all that, and gets recorded on either a flash drive or gets downloaded to the ground station on the satellite. There is a problem here also. As soon as the satellite, as soon as the rocket gets shut off, their major broadband transmission shuts off. They have only a very low rate transmission. And so you can only send back small amounts of data. So we have to somehow live through that, and we have to get useful data. Now signals at low Earth orbit, they are, I will not remain there. All I will say is that there is RFI from the Earth, which is much higher than these, and the natural sources themselves are at a lower background, and the omnipresent galactic background is there. And apart from that, auroral kilometric radiation, solar bursts, and lightnings are there. The natural sources, which are the payload, will be in the upper F layer of the ionosphere, which is about 350 to 400 kilometers. The attenuation due to the bottom of the ionosphere, I told you that the ionosphere acts like an attenuator. It stops radio waves from coming from outside. It stops radio waves going from inside. Nevertheless, the attenuation is not large enough. So the attenuated RFI will still come through significantly, but it will be slightly reduced. So the chance of detection from the sunlight side for stronger radiations from solar flares exists. So we can see those. Solar bursts
can be as high as 30 to 50 dB above the galactic background. So we may be able to see that too. So there are double objectives. In case we are lucky, we will not only see the RFI from the Earth, but we will also see some things from the sun and from the other objects in the sky. Now, coming to this antenna, I don't know whether you can see that. I don't have a pointer to show, but you can see two black rods projecting from the payload. I go there. You can see these two rods projecting, and that is the antenna. And this is the satellite after it has shed all the things. So this is the bay which is there. On the open bay, the antennas are supposed to be sitting there. And of course, these are the things which we were looking at earlier. This is the Earth's lightning and the solar bursts and all that. And so the sensitivity of reception of a radio wave is very much dependent upon the antenna length. As I don't know whether you can see the bottommost, the voltage which you get is proportional to the length of the antenna. But you cannot have a very large length of antenna which can be projected into space very easily from the satellite. So, although the antenna length decides the sensitivity, you have to be careful and you have to do something clever to match the antenna to the later amplifiers. You see, if I told you that a dipole antenna is half the wavelength. Now, why half the wavelength? Half the wavelength because that is the wavelength at which there is optimum impedance matching between the source and the load. And that is how what is called a power transfer theorem works in physics. So if you have a source and if you have a load and the source is feeding the load, if you do not have impedance matching between the two, then you do not get anything delivered. Everything gets reflected back. So in a receiver's, electronics receiver, it is important that the source load and the actual load, they match each other. They should be actually equal. And it so happens that the impedance which is projected by a dipole is of the order of 50 to 70 ohms. And so therefore, that is a perfect match. And that is why you will find even on your TVs and your various other receivers, it will say 50 ohm input impedance. It will say that somewhere if you if you look at it carefully. So this impedance matching goes for a toss when you reduce the length. If you keep reducing the length, it becomes what is called an infinitely small antenna. And an infinitely small antenna has very little radiation efficiency. It can receive very little power. So you need a mechanism to transfer this voltage, a few electrons which you are receiving from space, into actual voltage. You need some clever mechanism. And that is what is called an active antenna. So there is an active antenna here through the matching network, and then it forms a gain stage and it does the remaining things in a normal manner. So this is a troublesome thing, but it can be overcome. And the digital backend is the standard digital backend which is there in all cases. So there is baseband sampling and there is a dual 12-bit ADC and so on and so on. Sampling frequency is of the order of 33 megahertz because we want to observe only 16 megahertz up to. And it has a spectral resolution of about 16 kilohertz. These are for technical matters for anybody who is in the engineering area and who can easily understand that. So finally, a payload has been made, and that looks like this. It is only about 15 centimeter by 15 centimeter by 15 centimeter, actually slightly less. And this has, inside of that, we have the onboard computer, and it has the engineering programmable conditioner, and there's a digital backend, it has gain stages, and it has provision for ejecting these antennas into space. And so this is payload disassembled, and the antennas are projecting on both sides, and I'll show you how they come out. And this is how it will be orbiting. This is the Earth, imagine, and that is the satellite which is orbiting. And so it is a polar orbiting satellite, and which precises, and so it will cover the equatorial areas as well every day, and more than once. So it makes 1.5 hours, it makes one revolution. So it goes through about 16 revolutions in a day. And so that is the whole idea. So that is the South Pole, that is the North Pole, and this is the XYZ axis. So this is a stator antenna. The antenna is kept inside this box, packed. It is under tension, and it is kept by a hard nylon wire, and which has to be heated whenever it has to be released. And so once it is released, the springiness of that will come out. And you can see the extended antenna there, and I'll show you here. I hope this works. Does it work? Does it work? Okay, I'm sorry. Here. Oh, sorry. I did something. Now that is how it will deploy in space, and then it will continue to stay there. Now you might have seen that the whole thing shakes, right? So this question has been asked, but remember that the rocket is about few tons, about 1.5 tons or something like that, and this is 2 kg, and so we have calculated that it doesn't make any any great impact on the. Sorry. Yeah, so this is on the ground of our department on the terrace. The box is being tested, and this is what we find. This is how the spectrum looks. It looks terrible. Okay, you cannot find anything in space with this kind of spectrum. Okay, so we wondered what the hell is going on. So it was all because there is so much of interference all around us, we thought, but then we started cleaning up. That much of the interference we saw in the previous slide was emanating from self-generated RFI, from our own digital boards and our own DC-DC circuits, which we had employed. So we had to clean up this whole thing. And it takes a few years because it is so much of an effort to find out from where this is coming. And the boards have to be shielded, and then they have to be custom modeled, and then they have to be produced by a company which can actually produce such things. And so we have a partnership with SciComm in Pune, and with whom it took a few years and several rounds of revised design that were costly. So after we did the cleanup, the results are much better as seen below. And incidentally, we also got an interesting opportunity last year for experiments to be conducted in the polar Arctic radio quiet location this year. In fact, it was told in the IITM summary that they have an Arctic experiment going on. So we also got a chance to send our payload to the Arctic. And so this was, we presented our case, and then the review panel accepted that. And so our student trainee, Mr. Pawar, he was sent to the Himadri station last month. And he conducted experiments there for 1 month. And these efforts are shown also in the later. So this was how the spectrum was cleaned. And it is still, of course, receiving some signals, but they're all at a very low level, which is sort of reasonably satisfactory. I would have liked it to go much more down below, but this is about what we can do at this moment. And this is when the radio transmitter was off from the nearby broadcasting station. And this is what happens when the broadcasting station comes on. So it also provides a kind of a calibration. This is 792 kilohertz broadcast from All India Radio, which is nearby in the evening. And there are a few other things which are still not explained, but which is local. Then we took this to Arctic in October. The temperatures varied from about -5 degrees to -20 degrees centigrade. And we tested our payload, and this is what we got there. So the Himadri station is located in a purportedly RFI-free area. They advertise this in their website, that this is a very radio-quiet region. But I just want to tell you that there is no place on earth which is free from RFI. And that is demonstrated by this simple experiment. So this is 16th of October, 2024, Himadri at 74 degrees latitude, and the time is 20:53 night. And of course, it doesn't make a difference because it was all Arctic night, more or less. So I come to the summary of what we have been trying to do. We are now on the verge of launching a space mission to map the global RFI. We could then move forward on our moon quest and explore the Earth-Moon environment as well as the universe at very low frequencies. The solar and extrasolar radiations not only affect the Earth's nearby atmosphere and climate, but impinge on our magnetic fields and upper atmosphere as well as the exosphere. We have seen the connection between tropical atmosphere and the solar-Earth interaction, the Earth-Moon coupling, and many mysteries that are yet to be explored in the distant cosmos. New exploration in astronomy are continuing to be exciting, but it is clear that we live in an infinitely small and fragile and yet wonderful radiation-filled globe. I have some personal comments. Taking a space astronomy research projects in the university has been a very challenging experience. I didn't know that the Vice Chancellor will be sitting here. This is both because of serious funding issues as well as a constant churn of human resource. Of course, we can take pride that we trained a lot of people who are sitting in various places in the globe as postdoctoral fellows or people who have completed their PhDs and so on and so forth. While a majority of our students have left for either academic pursuits or gainful employment, continuity becomes difficult due to inadequate paperwork and experience gain being lost when the individual goes. In our case, the pandemic, of course, additionally caused havoc. Space projects need good financial backing over a period of 10 or more years to fructify, which is true in almost all the countries, and at least a few competent regular technical staff over many years for continuity. But notwithstanding these difficulties, we have managed to make good progress thanks to the high cooperation from the project students and the faculty and the university. I want to especially thank all of them. So we have currently Professor Aditi Joshi, who is the PA, and then Damayanti Garpure, who was the previous PA, and then myself. And then we have had a host of students. The list is very long, so this is only the more recent list. And all those who are marked red have already left, either for abroad or for employment. And we are left with just two guys just now. And of course, we have some consortium partners from Professors Deshpande, RRI, Janardhan from Physical Research Lab, Abhirup Datta from IIT Indore, and others who have joined this activity as COIs. They have enhanced our understanding about the overall goals and helped us in completing the engineering model. This was the recent 2019 batch, and they left in 22. Most of them left in 22. So now we have only Niketan and Aditi and Pawar, Some of them is remaining, but I couldn't get their photographs in short time. This was the thing which we started. These fellows are all either abroad or half of them have finished their PhDs, and they are in various places. Thank you very much.
Thank you, sir, for such a fascinating lecture on Earth, Moon, space exploration. Your insights have truly expanded our understanding of this fascinating field. Now, a quick question, if any.
I'll be happy to answer.
Hello, sir.
Yes.
As you said now,
yeah,
man-made RFI is high.
Yes.
That reaches from the Earth to the Moon.
To outwards, yes.
Are there any remedies to remove this from them? Can you use solar exploration in this case?
Yes, well, solar exploration is, first of all, let us understand. Solar exploration you can do from many aspects. You can, fortunately, from the, as I showed you, two windows. One is the optical window, through which you can, of course, see the outside. So you can have observatories which are solar telescope observatories on the ground, or you can have solar telescope observatories in space. There is one which has been launched some time ago by ISRO, which is called the Aditya spacecraft, which is sitting at L1, Lagrangian, okay, and which has been giving some results. People are still trying to understand many things from there. And there are other telescopes. There is Solar Dynamic Observatory, SDM. Then there is SOHO, which is probably getting shut down. And Stereo A, Stereo B, and so on and so forth. Many for observing sun continuously. Okay, because we need that information for the same purposes which Professor Moore explained, because we need to understand how much is the gamma ray flux which is coming, how much is the X-ray flux coming, and of course the radio flux coming. And we have radio observatories like GMRT and various other committed observatories like MWA and others. And so this is possible both from here and from outside the Earth's surface to observe the sun continuously. So we have 24-hour observatories, 24/7 observatories, monitoring the sun now. And so we get to know what is happening from the sun. And it is very important. Your question is very relevant, particularly with regard to the solar storms. These solar magnetic storms, as I told you, sun sends high energy charged particles, but sometimes there are huge eruptions on the sun. And as a result, you get massive storms. And these so-called extreme events, they can impact the magnetic field of the Earth. They can actually wipe out the magnetic field of the Earth for a short time. And in that process, the satellites which are sitting in the periphery of the Earth, some of them will get wiped off, okay, because they will all get killed by these high energy charged particles. These are called single particle events. And they are extremely, satellites are extremely vulnerable to that. So why these stereo and solar dynamic observatory are sitting there watching the sun 24 hours of the day is because you can get about an hour to half an hour of advance notice on this solar magnetic storm coming towards the Earth. And in the process, you can shut down all these satellites, their power systems and so on. And not only that, the high voltage power systems on the Earth, like say 10 megawatts upwards, these are very vulnerable to the geomagnetically induced currents and geomagnetically induced voltages. And we came to know about this about 40 years ago. I was just doing my postdoctoral, and that's when we realized in 1989 there was a massive storm, and which put out the put out a huge transformer system in Canada. It took about 15 seconds for the huge transformer. I think I don't remember the megawatts, but it was not less than 10 megawatt. 10 megawatt transformer was reduced to ashes, because of the geomagnetically induced currents. No, I'm talking of a completely different frequency. Okay, I'm not talking of that. That is almost a DC current which is flowing. Okay, the geomagnetically induced current is a current which is forced upon the Earth's high voltage transmission lines, and which is a current which is almost 0 hertz. Okay, and therefore it is able to flow through to the transformer and the core and heat it and burn it. So that's what happens. So the observations of sun are extremely important, continuously. I hope I answered you.
Do we have another question time?
Yeah.
Please be quick.
Okay, sir. Sir, this way.
Oh, okay.
Yeah, so this question is not exactly related to today's talk, but I always wanted to ask this to a radio astronomer.
Yeah.
Back in 1970s,
Yes.
one extraterrestrial radio signal was recorded in
Yeah.
USA. And it is nicknamed as WOW
Wow.
signal. Yes. I read it from popular science journal and TV shows. So
Yeah.
they never explain what is the
Yeah.
scientific significance of that.
Yeah.
So my question is there any scientific significance of this signal?
No.
Nothing.
Nothing.
Okay.
Nothing so far because we have not understood. There are so many things which we don't understand. Okay. Yeah, of course, because that was the only signal which was received in all these 50 years. So that is why. Anybody else? Yeah, please. Oh.
Thank you so much, sir. We will now proceed with the merit certificate ceremony. We would now like to once again invite our esteemed guests to the stage to present the certificates. May I request the Honorable Secretary of the Ministry of Earth Sciences, Dr. Ravi Chandran, the chief guest of today's program, Professor Baryon Moore, the guest of honor of today's program, Professor S. Anand Krishnan, Dr. R. Krishnan, Director, Indian Institute of Tropical Meteorology. Please take your seats, sir.
अब वो समय आ गया है जिसका आप सभी लोगों को बेसब्री से इंतजार था। आज इस संस्थान के स्थापना दिवस के 63 वर्ष पूर्ण हो रहे हैं। हमें कई प्रतिभाशाली वैज्ञानिकों और प्रतिबद्ध सहायक कर्मचारियों के प्रयासों से संभव हुए समर्पण, कड़ी मेहनत और सहयोग के 63 वर्षों का जश्न मनाने का पर्व है। इस अवसर पर हम कुछ ऐसी व्यक्तियों को सम्मानित करते हैं जिन्होंने वास्तव में अपना योगदान देकर इस संस्थान में उत्कृष्ट प्रदर्शन किया है। इस वर्ष हम उनकी असाधारण उपलब्धियों का सम्मान 5 अलग अलग श्रेणियों में सर्वश्रेष्ठ कर्मचारी सम्मान चिन्ह एवं प्रमाण पत्र 2024 प्रदान करके कर रहे हैं।
It is now my pleasure to invite our Honorable Secretary, Dr. M. Ravi Chandran, to present the Certificate of Merit to our deserving honorees for their outstanding contribution to weather and climate science. But before we proceed, sir, I request to felicitate Dr. Roxy Matthew Cole, Senior Scientist, for his prestigious achievement. This is indeed a proud moment for IITM.
Roxy, sir.
Dr. Roxy Matthew Cole of IITM Pune has been honored with the prestigious Rashtriya Vigyan Puraskar, Vigyan Yuva Shanti Swarup Bhatnagar Award for the year 2024 in the earth science domain. It is the highest distinction which is presented to him by the Honorable President of India, Srimati Draupadi Murmu. Congratulations.
thank you very much. Thanks to the IITM family and my own family. Thanks a lot. It's a fruit of our collective efforts, and we will progress more. Thank you.
अब मैं 2024 में शोध कार्य में उत्कृष्ट कार्य करने वाले कर्मचारियों को मंच पर एक एक करके आमंत्रित करूंगा सम्मान चिन्ह एवं प्रमाण पत्र मौसम और जलवायु विज्ञान के लिए। साथ ही उन्होंने किस क्षेत्र में कार्यरत हैं ये भी बताऊंगा। मैं डॉक्टर रविचंद्रन सर से आग्रह करता हूं कि उनको ये पुरस्कार दें। पहला, इस क्षेत्र में पहला नाम डॉक्टर SD पवार, वैज्ञानिक जी, एटमॉस्फेरिक इलेक्ट्रिसिटी में कार्यरत। यू ओनली सर, आप। अगले क्रम में डॉक्टर जे संजय, वैज्ञानिक F, रीजनल क्लाइमेट मॉडलिंग। उसके बाद डॉक्टर सुवर्णा फडणवीस, वैज्ञानिक F, एटमॉस्फेरिक केमिस्ट्री एंड डायनेमिक्स। आगे तैयार हैं डॉक्टर रमेश वेल्लोर सर। तालियां बजती रहनी चाहिए। डॉक्टर रमेश वेल्लोर, वैज्ञानिक F, एटमॉस्फेरिक डायनेमिक्स, ग्लोबल एंड रीजनल मॉडलिंग। डॉक्टर मधुचंद्र रेड्डी, डॉक्टर मधुचंद्र रेड्डी, वैज्ञानिक F, रिमोट सेंसिंग इन एटमॉस्फेयर, क्लाउड एंड प्रेसिपिटेशन स्टडीज। डॉक्टर हमजा, डॉक्टर हमजा, वैज्ञानिक F, मॉनसून वेरिएबिलिटी, क्लाइमेट चेंज एंड डायनेमिक्स। तालियां बजाते रहिए सबके लिए। अगले इसके बाद डॉक्टर सचिन देशपांडे, डॉक्टर हमजा अवार्ड लेते हुए। डॉक्टर सचिन देशपांडे, वैज्ञानिक F, एटमॉस्फेरिक रिसर्च टेस्ट बेड एंड रिमोट सेंसिंग। इसके बाद डॉक्टर श्रीमती प्रीति भास्कर, वैज्ञानिक F। डॉक्टर श्रीमती प्रीति भास्कर। इसके बाद डॉक्टर सुब्रता कुमार दास, वैज्ञानिक F, मेसो स्केल मेट्रोलॉजी। वो शायद हमारे बीच उपस्थित नहीं हो सके हैं। डॉक्टर अभिलाष पानीकर, वैज्ञानिक E, एरोजॉल रेडिएटिव एंड क्लाउड इंटरेक्शन स्टडीज। इसके बाद डॉक्टर फनी मुरली कृष्ण, डॉक्टर अभिलाष पानीकर अवार्ड लेते हुए। डॉक्टर फनी मुरली कृष्ण, वैज्ञानिक E, एटमॉस्फेरिक मॉडलिंग, HPC कंप्यूटिंग। इसके बाद डॉक्टर महेंद्र कन्वर। उसके बाद डॉक्टर जयराम। डॉक्टर महेंद्र कन्वर, वैज्ञानिक E, क्लाउड एंड रेन माइक्रोफिजिक्स। इसके बाद डॉक्टर जयराव सर, डॉक्टर महेंद्र कन्वर सर प्रमाण पत्र लेते हुए। डॉक्टर जयराव, वैज्ञानिक E, कैरेक्टराइजेशन ऑफ एरोजोल्स। इसके बाद डॉक्टर राहुल रेड्डी, वैज्ञानिक E, एटमॉस्फेरिक एरोजोल्स। डॉक्टर जयराव सर अवार्ड लेते हुए। तालियां बजाते रहिए। डॉक्टर राहुल रेड्डी, वैज्ञानिक ई। इसके बाद डॉक्टर श्रीमती लीना पीपी, वैज्ञानिक ई, क्लाउड फिजिक्स एंड एटमॉस्फेरिक डायनेमिक्स। इसके बाद श्री लबिन टीआर, तालियां बजाते रहिए। ये वही लोग हैं जिनके अंदर हमने कार्य किया है, अपने शोध कार्य। श्रीमती लीना पीपी, वैज्ञानिक ई, श्री लिबिन टीआर, वैज्ञानिक ई, एटमॉस्फेरिक इंस्ट्रूमेंटेशन। इसके बाद डॉक्टर श्रीमती अयंतिका डे चौधरी, वैज्ञानिक ई, डायनेमिक्स एंड वेरिएबिलिटी ऑफ साउथ एशियन मॉनसून। उनके बाद श्रीमती अर्चना राय, डॉक्टर अयंतिका डे चौधरी, वैज्ञानिक ई, श्रीमती अर्चना राय, वैज्ञानिक डी, लैंड सरफेस प्रोसेसेस। इसके बाद डॉक्टर अभिजीत डे। उसके बाद डॉक्टर शहादत सरकार, श्रीमती अर्चना राय, वैज्ञानिक डी, डॉक्टर अभिजीत डे, वैज्ञानिक डी, इंट्रा सीजनल वेरिएबिलिटी ऑफ इंडियन समर मॉनसून। शहादत सरकार सर, उसके बाद गौरव गोवर्धन। अगले क्रम में डॉक्टर शहादत सरकार, वैज्ञानिक डी, न्यूमेरिकल मॉडलिंग एटमॉस्फेरिक स्केल इंटरेक्शन मॉनसून वेरिएबिलिटी। इसके बाद डॉक्टर गौरव गोवर्धन, डॉक्टर गौरव गोवर्धन। तालियां। डॉक्टर गौरव गोवर्धन, साइंटिस्ट डी, एटमॉस्फेरिक केमिस्ट्री एंड फॉग। अगले क्रम में हम एक प्रमुख श्रेणी में सम्मान चिन्ह देना चाहेंगे जिसकी चर्चा किए बगैर यह सम्मान अधूरा है, जो है सर्टिफिकेट ऑफ रिकॉग्नाइजेशन फॉर मिशन कर्मयोगी लीडर 2024। नाम इसे जाता है श्री नीलेश नारायण वाघ, परियोजना वैज्ञानिक 2। नीलेश नारायण वाघ। उपस्थित नहीं हो सके।
It is now my pleasure to invite our esteemed chief guest, Professor Berrien Moore, to present the certificate of merit to our deserving honorees for their outstanding contribution as administrative and project staff. To begin with, Best Employee Merit Certificate 2024 for the administrative staff category, and the names are Srimati Vijaya Kumari, Administrative Officer 3, for exemplary contribution to administrative matters, followed by Shri Dilip Shinde ji, Srimati Vijaya Kumari, Shri Dilip Shinde ji to be coming next. Shri Dilip Shinde ji, Section Officer for outstanding contribution to Director's Secretariat. Srimati Bhavana Naik, Section Officer. The next award goes to Srimati Bhavana Naik, Section Officer for outstanding contribution to establishment matters. श्रीमती कविता भारती, next we have Srimati Kavita Bharti, Section Officer for outstanding contribution to financial management. श्रीमती ज्योति वागले, The next award goes to Srimati Jyoti Wagle, Upper Division Clerk, for outstanding contribution to establishment matters. Srimati Jyoti Wagle. Shri B.T. Pawar ji. The next award goes to Shri B.T. Pawar, Junior Executive, for outstanding contribution to procurement matters. The next set of Best Employee Merit Certificate 2024 in the Project Staff category, and the names are Shri Amey Date, Project Scientist 2, for outstanding contribution to Center for Climate Change Research. Shri Amey Date. Next in line, Shri Yang Lian. Shri Yang Lian, Project Scientist 1, for outstanding contribution to Atmospheric Research Test Bed, Central India. Shri Yang Lian getting the award. Please, we need to hear a big round of applause. Shri Rohit Patil ji. Shri Rohit Patil, Project Scientist 1, for outstanding contribution to High Altitude Cloud Physics Laboratory. Big round of applause, everyone. Shri Sunil Khadgarai, Project Scientist 2, for outstanding contribution to Mesoscale Rain Gauge Network, Mumbai. Let the claps keep flowing. Dr. Roshmita Panda next. Shri Sunil getting the award. Dr. Roshmita Panda. Dr. Roshmita Panda, Project Scientist 2, for outstanding contribution to climate variability and prediction. Be generous with your claps, ladies and gentlemen. Dr. Revant Reddy to come up next. Dr. Revant Reddy, Project Scientist 2, for outstanding contribution to National Monsoon Mission. Next in line, Shri Mahesh Nikam, Project Scientist 1. Shri Mahesh Nikam, Project Scientist 1, for outstanding contribution to lower atmospheric research using unmanned aerial system facility. A big round of applause, everyone, to this set of awardees. Now, Dr. Abhishek Gupta, Project Scientist 2, for outstanding contribution to cloud aerosol interaction and participation enhancement. Next in line, Srimati Rashmi Sahu, Senior Project Associate, for outstanding contribution to library information and publication. Can we still hear the claps? Thank you so much. Srimati Rashmi Sahu taking the award. Shri Abhijit Gangarne, Project Scientist 1, for outstanding contribution to thunderstorm dynamics. Dr. Rajesh Kumar, can we have you? Dr. Abhijit taking the award. Next, Dr. Rajesh Kumar Singh Maurya, Project Scientist 3, for outstanding contribution in National Monsoon Mission. Next, can we have Shri Mahesh Kalsetti, Project Scientist 2, for outstanding contribution to National Monsoon Mission. Next in line, Shri Praful Prakash, Shri Mahesh Kalsetti taking the award. Shri Prakul Prakash Yadav, Project Scientist 1, for outstanding contribution to Metropolitan Air Quality and Weather Forecasting Services. Next in line is Srimati Pradnya. Thank you. The next award goes to Srimati Pradnya Suryavanshi, Section Officer, for outstanding contribution to General Administration Section. A big round of applause, ladies and gentlemen. Thank you. Thank you, sir. Please take your seats. It is now my pleasure to invite our esteemed guest of honor, Professor S. Ananthakrishnan, to present the certificates of merit to our deserving honorees for their outstanding contribution. Over to Abhishek.
इसी क्रम में आगे बढ़ते हुए हिंदी में योगदान देने के लिए सर्वश्रेष्ठ कर्मचारी सम्मान चिन्ह एवं प्रमाण पत्र 2024 जाता है श्री मृगांक शेखर विश्वास, वैज्ञानिक डी। इसके बाद श्री I.A. पठान, श्री मृगांक शेखर विश्वास सम्मान चिन्ह लेते हुए श्री I.A. पठान, अनुभाग अधिकारी। उसके बाद श्री उमेश ढोंडीराम घाटल जी, पठान जी पुरस्कार सम्मान चिन्ह लेते हुए श्री उमेश ढोंडीराम घाटल जी, अपर डिवीजन क्लर्क। इसके बाद श्रीमती अश्विनी ढिंडले जी, श्री उमेश जी, अपर डिवीजन क्लर्क, सम्मान चिन्ह लेते हुए श्रीमती अश्विनी ढिंडले जी, आउटसोर्स कर्मचारी। अगली श्रेणी में आगे बढ़ते हुए IITM में जिन्होंने उत्कृष्ट प्रदर्शन किया है ऐसे संविदा कर्मचारियों को सम्मान चिन्ह एवं प्रमाण पत्र 2024 से सम्मानित किया जाएगा। उनके नाम हैं श्री अमर सिंधे जी, उसके बाद सुश्री शोभा डावरे जी, शोभा डावरे जी, तालियां बजती रहनी चाहिए। इसके अगले क्रम में सुश्री अश्विनी पेंढारकर जी, उसके बाद श्री संजय मेचकर जी। शोभा डावरे जी सम्मान चिन्ह लेते हुए सुश्री अश्विनी पेंढारकर जी, उसके बाद श्री संजय मेचकर जी, श्री संजय मेचकर जी अगले क्रम में। उसके बाद श्री शुनुई कुरहाड़कर जी, उसके बाद तैयार रहेंगे श्री निकालजे संतोष जी। अगले क्रम में श्री निकालजे संतोष जी, उसके अगले क्रम में श्री संदीप अब्बा सोनवड़े जी, निकालजे संतोष जी सम्मान चिन्ह लेते हुए, श्री संदीप अब्बा सोनावड़े जी। इनके अगले क्रम में रहेंगे श्रीमती वैशाली पाठक जी। श्रीमती वैशाली पाठक जी, इस क्रम को आगे बढ़ाते हुए इस क्रम को आगे बढ़ाते हुए 2 और अनुभाग को उत्कृष्ट प्रदर्शन सम्मान चिन्ह दिया जा रहा है, जो इस प्रकार है। आप लोग पहले से ही गेस कर सकते हैं। पहला है सामान्य प्रशासन अनुभाग, स्वच्छता मिशन 2024 के अंतर्गत स्वच्छता ही सेवा अभियान के लिए मैं सामान्य प्रशासन प्रभारी और उनकी टीम को पुरस्कार सम्मान चिन्ह लेने के लिए आमंत्रित करता हूं। हम सभी लोग जब कभी भी अपने कार्यालय में जाते हैं, हमेशा पाते हैं कि IITM परिसर कितना स्वच्छ है। कोई भी उत्सव हो, ये स्वच्छता कर्मचारी हमेशा उपलब्ध रहते हैं। ये हमारे वो हीरोज़ हैं जिनकी चर्चा हमेशा कम होती है, किंतु इनका कार्य अतुलनीय है। ये सभी अनसंग हीरोज़ के लिए जोरदार तालियां, एक बार खड़े होकर जोरदार तालियां बजा दीजिए। सभी लोग खड़े होकर जोरदार तालियां इनके लिए बजाइए। ये स्वच्छता कर्मचारी हैं। अगले क्रम में दूसरा अनुभाग जिसे बिल्कुल भी भूला नहीं जा सकता, वो है सुरक्षा अनुभाग। 24 घंटे समर्पित रूप से काम करने और एक सुरक्षित अनुकूल वातावरण प्रदान करने के लिए मैं सुरक्षा अधिकारी प्रभारी और इनकी टीम को आमंत्रित करता हूं कि वो आएं और सम्मान चिन्ह ग्रहण करें। इस अनुभाग को तो भूला ही नहीं जा सकता। ये सभी लोग 24 घंटे अपने काम के प्रति समर्पित रहते हैं। IITM हमेशा एक आनंददायक वातावरण बनाए रखते हैं। ये लोग भी हमारे वो हीरोज़ हैं जिनकी चर्चा कम ही होती है, किंतु इनका कार्य भी अतुलनीय है। इन हीरोज़ के लिए भी जोरदार तालियां। कृपया इनके लिए भी अपने स्थान पर खड़े होकर स्टैंडिंग ओवेशन दें।
It is now my pleasure to invite our director, Dr. Krishnan, to felicitate our retired employees, those who have completed 75 years of age, and also the employees who have completed 25 years of service at IITM.
इस संस्थान में 75 वर्ष पूर्ण करने वाले सेवानिवृत्त कर्मचारियों को शॉल एवं श्रीफल से सम्मानित किया जाता है। निम्नलिखित कर्मचारियों ने 75 वर्ष पूर्ण कर लिए हैं, मैं उनके नाम हैं, किंतु उसके पहले इनके विभागों के नाम जो मैं लूँगा वो आज के विभागों के नाम से अलग हो सकते हैं। पहला है श्रीमती SP लकड़े जी, ये हमारे बीच उपस्थित नहीं हो पाई हैं। दूसरा श्रीमती UL भंडारी जी, ये भी हमारे बीच उपस्थित नहीं हो पाई हैं। तीसरा श्री VS कुलकर्णी जी, परचेस एंड स्टोर्स। तालियां बजाइए। तालियां बजती रहनी चाहिए। ये वो उम्र है जो हम सबको अचीव करना है, इसलिए तालियां बजती रहनी चाहिए। इसके अगले क्रम में श्री DR कुम्हार जी, ये भी हमारे बीच उपस्थित नहीं हो पाए हैं। डॉक्टर DB जाधव जी, ये भी हमारे बीच उपस्थित नहीं हो पाए हैं। श्री SK जाधव जी, क्लाइमेटोलॉजी एंड हाइड्रोलॉजी। श्री KK अबनवे जी, वो भी हमारे बीच उपस्थित नहीं हो पाए हैं। जादव जी सम्मान लेते हुए। उसके आगे श्रीमती NS गिरजा जी, ये भी हमारे बीच उपस्थित नहीं हो पाई हैं। आगे श्रीमती SB शर्मा जी, ये भी उपस्थित नहीं हो पाई हैं। श्री PV पुराणिक जी, फोरकास्टिंग एंड रिसर्च डिवीजन। तालियां बजाते रहिए। आगे डॉक्टर NA सोनटक्के जी, ये भी हमारे बीच उपस्थित नहीं हो पाए। श्री SC रहालकर जी, LIP डिवीज़न, इन्होंने IITM में कार्य किया किंतु ये पेंशनर IMD के हैं। आमंत्रित करता हूं। तालियां बजाते रहिए, अभी कुछ और अवार्ड्स बाकी हैं। इसके अगले क्रम में इसके अगले क्रम में इसके अगले क्रम में 25 वर्षों की सेवा पूरी करने वाले कर्मचारी को कलाई घड़ी स्मृति चिन्ह स्वरूप दी जा रही है। मैं जिनका नाम लेने वाला हूं, उन 10 कर्मचारियों ने 25 वर्ष की सेवा इस संस्थान में पूर्ण कर ली है। कृपया वो मंच पर आएं और अपना स्मृति चिन्ह ग्रहण करें। उनके नाम है डॉक्टर जयराव, इसके बाद डॉक्टर C ज्ञानशीलन, डॉक्टर जयराव सर, डॉक्टर C ज्ञानशीलन सर। इसके अगले क्रम में डॉक्टर श्रीमती पद्मा कुमारी मैडम, वो उपस्थित नहीं हो सकी। डॉक्टर देवेंद्र सिंह सर उपस्थित नहीं हो सके। श्री M महाकुर जी, उनके अगले क्रम में रहेंगे श्री सुनील मनोहर सोनभावने जी। श्री महाकुर जी, तालियां बजाते रहिए। श्री सुनील सोनभावने जी, इनके अगले क्रम में डॉक्टर सुमारू राम जी, डॉक्टर सुमारू राम जी। इसके अगले क्रम में रहेंगे डॉक्टर SK साहा जी, डॉक्टर सुमारू राम जी स्मृति चिन्ह लेते हुए। डॉक्टर SK साहा जी। इसके आगे रहेंगे श्री राकेश भंडारी दिल्ली ब्रांच, जो अभी उपस्थित नहीं हो सके हैं। और आज के लिए अंतिम स्मृति चिन्ह ग्रहण करेंगे डॉक्टर H नरेंद्र सिंह जी। धन्यवाद। एक और है श्री नीलेश वाघ जी यहाँ पे आ गए हैं, जिनके लिए कर्मयोगी लीडर 2024 पुरस्कार सम्मान चिन्ह दिया जा रहा है। उनका सर्टिफिकेट, वो अपना प्रमाण पत्र ग्रहण करें। धन्यवाद सर, कृपया आप अपना सीट ग्रहण करें।
Shri Ralkar ji wants to say a few words.
Please
Please
take your
be
seat,
seated,
sir.
sir.
Yeah, please.
Thank you for giving me opportunity. On my behalf and on behalf of retired my companion colleagues, I am appearing before you. Honorable Director, sir, we are retired before 15 years back. By heart, we accept your felicitations. Thank you so much. I want to give best wishes to my institute. I pray, let Almighty God may prosper IITM in constant ascending order till sun moon exist. Last point, but not least, I pray, let Almighty God give all of you a healthy, wealthy, prosperous, and excellent, and a long, enjoyable life along with family members. With these words, I come to it. Thank you very much. Have a good day.
धन्यवाद सर।
We are now at the concluding part of our event. It is my pleasure to invite Dr. Tara Prabhakaran, Senior Scientist at IITM, to deliver the vote of thanks. Thank you.
Namaste. Are you all here? Yes. So let us first thank two people, Dr. Amita Prabhu and Abhishek Gupta. Please give them a round of applause for comparing this whole session. Okay, so now I continue my vote of thanks. So our Honorable Secretary, Ministry of Earth Sciences, Dr. M. Ravichandran, our Chief Guest, Professor Berrien Moore, Dean, College of Atmospheric and Geographic Sciences, and Director, National Weather Center, and at the University of Oklahoma, Norman, USA, and guest of honor, Professor S. Anandakrishnan, INSA Senior Scientist, and Adjunct Professor at Savitribai Phule University, Pune, and former Director of GMRT Pune, respected Dr. R. Krishnan, Director of IITM, and all previous directors and online participants and my dear IITM family members. Actually, it is a great honor and privilege for me to extend a very hearty vote of thanks to all of you on this 63rd Foundation Day of our beloved institute. On behalf of the entire IITM family, I convey sincere gratitude to our honorable delegates and to each one of you who are present here for this togetherness. How much did we like that was such a celebratory moment just before and gracing this particular occasion. I must express wholehearted thanks to our Honorable Secretary, MOES, Dr. M. Ravichandran, who supported us immensely to meet our endeavors and continue to motivate us, inspire us, and to strive for excellence. Sir, your energy is unwavering and transparent to all of us. And your encouragement puts us in the immense progress and wish for something we could reach. We could do something much more better in our research at IITM. It is an immense pleasure to thank honorable chief guest, Professor Berrien Moore. He is the Dean, College of Atmospheric and Geographic Sciences, Director, National Center, University of Oklahoma, Norman, USA, for accepting our invitation and be present with us today and delivering a very enlightening talk. Professor Moore, your participation has introduced an exemplary charm and made this event more special for all of us. And special thanks for illuminating lecture and on the GeoCarp mission and science-based, he talked about science-based mitigation and adaptation and on climate change and science and sustainability. We need to change the feel-good strategy. This is a message he has given to us. And think of systems cascading problems and have courage to address this. And we are extremely grateful to our guest of honor, Professor S. Anandakrishnan, INSA Senior Scientist, Adjunct Professor, SPPU Pune, and former Director of GMRT Pune, who has always been inspirational for all of us through his interactions, continuous interactions with us. And thank you, sir, for being here and also delivering a fantastic talk on Earth, Moon, space exploration and their recent achievements. Although lengthy journey of seems, but with lots of progress he presented. And now we are blessed with also the presence of Vice Chancellor of Savitribai Phule Pune University, Professor Suresh Gosavi, sir. And it was a surprise, and thank you, sir, for being with us. And Professor Tirumala Venkateshan, who is part of the US delegation here, he is also with us, and charismatic and I must say, charismatic and inspirational and exceptional teacher, Dr. A.K. Kamra. And my teacher, same way my teacher, Dr. Pradeep Kumar, all present here. Thank you. And Dr. Rup Kumar Kohli and Kamaljit Ray Madam and Sinare sir, various other delegates here. Thank you for being along with us. On behalf of all of us, I would like to take this opportunity to express my sincere gratitude to our dear director, Dr. R. Krishnan, for his continued guidance and encouragements and able leadership, which is taking IITM to newer heights. And congratulations to all awardees. It was such a celebratory mood here of various categories. You make us all proud. And please enjoy the day fullest today. And I also extend my gratitude to Dr. S.D. Pawar and Dr. Sachin Deshpande as the chair and co-chair of the committee of this Foundation Day celebration, and Dr. and Sri Ajit Prasad for overall coordination of the event. And a sincere gratitude to all members of various committees that includes reception, hall management, catering, publication, purchase, cultural and transport. If something is missed, please forgive me. And it is your collective effort and hard work that made this event possible and so special. A very special thanks to administration, general administration and supporting staff for a smooth execution of the Foundation Day celebrations. Finally, I remember our founding director and father of our tropical meteorology, Professor P.R. Pisharity, and seek his blessings for all of us for this auspicious day. I also thank retired scientists and staff of IITM. I also remember those who could not make it here today, And finally, I acknowledge the media and press for their support. And thank you, Dhanyavad, and Jai Hind. Have a wonderful day and enjoy everything, every bit of it. Thank you so much.
Thank you, ma'am, for your kind words.
एक जोरदार तालियां उन लोगों के लिए जिन्होंने पीछे से लाके हम सभी को यहाँ पे स्मृति चिन्ह दिया है.
Rashmi Kakatkar and team. As we conclude this event, I kindly request everyone to rise for the national anthem.
सभी लोग सावधान. सॉरी, रियली सॉरी.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता. पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा. विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा. तव शुभ नामे जागे तव शुभ आशीष मांगे. गाहे तव जय गाथा. जन गण मंगलदायक जय हे भारत भाग्य विधाता. जय हे जय हे जय हे जय 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 हे.
विश्राम.
जय.
बस अब 5 मिनट और मैं आप सभी लोगों का लूंगा. सर कृपया अपनी सीट पे बैठ जाइए. आज 63वें स्थापना IITM स्थापना दिवस मनाने के लिए हम सभी लोग यहाँ शामिल हुए. इसके लिए आप सभी का धन्यवाद. हम आशा करते हैं कि आपको यह सभी प्रोग्राम कार्यक्रम अत्यंत बहुत अच्छा लगा होगा. अब मैं आगे बढ़ता हूँ. आज शाम में भी एक कार्यक्रम होने वाला है. मैम, आपको पता होगा ना आज शाम को क्या होने वाला है?
जी नहीं.
तो आज
खास होने वाला है.
हाँ, आज पद्म विभूषण स्वर्गीय पंडित बिरजू महाराज जी, जिनका नाम मुझे लगता है आप सभी लोगों ने सुना ही होगा.
हाँ, उनका नाम किसने नहीं सुना.
आज पद्म विभूषण स्वर्गीय पंडित बिरजू महाराज की विरासत को आगे बढ़ाते हुए लखनऊ घराना आज की संध्या विरासत की शाम की प्रस्तुति करने जा रहा है. यह कथक की प्रस्तुति के साथ साथ भिन्न भिन्न यंत्रों की जुगलबंदी होगी. आप सभी लोग सपरिवार आज संध्या 6 बजे इसी हॉल में इस सांस्कृतिक कार्यक्रम और उसके बाद रात्रि भोज के लिए आमंत्रित हैं. और मैं ये कह सकता हूँ दावे के साथ कि आज की विरासत की शाम ऐसी होगी जो आपने ना कभी देखी होगी ना कहीं सुनी होगी. तो आइएगा जरूर.
Thank you everyone for joining us today in celebrating the 63rd IITM Foundation Day. We hope you had a wonderful time and leave here feeling inspired and enriched. We are pleased to extend a warm invitation to you and your family to join us for the grand cultural program named Evening of Heritage, which is going to take place today at 6 p.m. at Megdot Hall, followed by a sumptuous dinner. We look forward to your presence and celebration with us.
अब मैं आप सभी को भोजन के लिए आमंत्रित करता हूं. इसकी व्यवस्था 3 जगहों पे की गई है. कैंटीन में, उसके सामने लॉन में एवं मेघदूत के बेसमेंट में. आप सभी लोगों का दिन शुभ हो.
And now it's time to enjoy a delicious lunch together, fostering friendships and collaborations at 3 different locations: canteen, lawn in front of the canteen, and at the basement of Meghdut Hall. The lunch for our dignitaries would be arranged at the guest house.